morning to all the participants. Our Anandaji at Guwahati. Welcome you, sir. I made you the presenter, so you can unmute yourself, sir, please. You can unmute. You can unmute yourself, sir. Yes, sir. Yes, sir. Now it is. Welcome you, sir.
From this PC actually it is not connected. Just can you give me 1 minute? I am to try actually from another PC. So here it is not audible.
Okay. So you are audible now.
Now it is audible.
Yes, sir. Yes, sir. Yes, sir. So we welcome you, sir. So dear participant, our this session expert, Professor Manadasji from IIT Guwahati has joined us. So before requesting him to share his views in his research domain, I would like to share some brief about him with you all. Professor Manadas is working in the Department of Mechanical Engineering at IIT Guwahati. He received his doctorates from IIT Kanpur in the domain of advanced manufacturing processes. His research areas includes the advanced finishing processes, nano finishing processes, the magnetorheological finishing, hybrid manufacturing processes, micro manufacturing, and so on. So far, he has published about 40 articles in various international and national journals. He also published about 50 articles in conference papers. He has so far written 15 book chapters and one book published in the domain of surface finishing. He has guided 4 PhD so far, and presently there are 8 PhD students are doing research under his kind supervision. So there is a lot of more to say about Professor Dasji, but because of the time constraint, I would like to express my welcome to Professor Das to share his views. Sir, you are welcome, sir. Please.
Thank you, Professor Ravi Pratap Singh, for giving such a nice introduction. Also, thank you to the committee for giving me opportunity for this nice talk. So, thank you again. So now I'm going to talk on this actually nano finishing of prosthetic implants and further tribological characteristics. Is it audible, Professor?
Yes, sir.
Is it
you are very clearly audible, sir, and slides are very clearly visible.
Okay, thank you. Now, actually, this is so. Let me. Okay, so in this slide, actually, I'm going to show what we are doing in our lab. So first slide here, you can see here in the first slide here, we are polishing that prosthetic implant, what we are going to show here. So this is a CNC machine here, actually we are using, it has a, all CNC machine, it has a 3 axis. So here actually there is a 4th axis is there. You can see there is a chuck. So this chuck actually it is used for holding the workpiece and it can be rotated up to 5 RPM. Okay, so by that actually this total 4 axis we can polish any complicated surfaces. Okay, so now we are purchasing one 5 axis CNC machine. With that 5 axis CNC machine, you know, actually any kind of surfaces can be polished, any complicated surface. So second one, this one is the actually plasma polishing setup. So we have a collaboration with ISRO Trivandrum. They have actually one unit, IISU, okay, issue inertial sensing unit. So they are using this plasma polishing for HRG Zyro. This kind of prismatic Zyro is there. So you can see this is a very small product. Actually, it is made of quartz, and the thickness is actually just 1 millimeter only. Uh, this kind of small this workpiece they are actually polishing because it is made from a rod, and after that actually as this quartz actually it is brittle material, so it is made from a brittle material, and then by a 5 axis CNC machine, vibration assisted CNC machine, they actually given this kind of shape, and lots of cracks are there in this surface. So to remove these cracks, actually they are using plasma polishing, and we have developed setup here actually in our lab for polishing this kind of components. Okay, so this third one here, you can see here, this is the magnetoreological abrasive flow finishing process. So after that, actually, it is retrofitted, and then again rotational MRF process. We shall discuss all these things here. And other than that, actually, this is the MRF setup, magnetoreological finishing setup here. So and then this one, actually, this in the middle, you can see it is a micro ECM setup. We have developed here in our lab this micro ECM setup. Now that more higher version also it is there, although the picture is not given here. And here you can see this is the tool here. As the tool is actually rotated, we are using the through a brass. So this is made of graphite and silver. So using this brass, actually we are providing current to that micro tool. And these kind of small gears, actually it is polished by this magnetoreological abrasive finishing process. Currently, we have developed one micro ATM setup also in our lab. So one PhD scholar he is working on that micro ATM setup. Other than that, actually we are doing work in the laser welding process. One PhD student already completed on laser welding. And then high-speed machining also, we have one PhD student has completed in high-speed machining. Okay, so this is the overview of our lab. So now uh, this is the outline of my presentation. I shall discuss about this, what is MR fluid actually basically, so that you can also develop this kind of MR fluid in your lab, and you can develop this kind of small setup in your own. So these are not that much costly. So you can develop in our lab also. And so we have developed couple of setup for this magnetoreological for polishing using this MR fluid. So these are actually magnetoreological finishing, magnetoreological abrasive finishing process, and rotational MRF process, magnetic field assisted finishing process. And I shall show actually few experimental investigation which we did in our lab, and then modeling simulation if we get time, then I shall show, and also we shall show actually this prosthetic implant which we have taken. It is made of actually titanium alloy of grade 5. So that finishing of this prosthetic implant and further characterization, tribological characterization, we did in our lab, that we shall show. Okay. And now, first actually we need why this kind of advanced finishing process is required. Basically, actually, whatever these conventional finishing processes, these are basically they are labor intensive actually. So like honing, lapping, grinding, this kind of setups are there. But honing and this grinding, actually, it is very difficult to do these complex preform surfaces. That whatever knee joint we have shown there, actually, this it is very difficult to polish this kind of complex preform surface by using honing and grinding process. So actually lapping little bit actually it is used. So there sometimes people use actually robotic arm, or sometimes people manual labor is used. But what happens actually whenever this technician or this technical people, those who are expert in polishing of this kind of work pieces, complex work pieces, so in the details actually that company faces lots of problems. So for polishing this kind of complex freeform surfaces, complex geometrical shapes is very difficult nowadays. So that's why these advanced finishing processes are required. And also we want to make this advanced finishing process actually this automatic, and we want to get rid of this labor intensive nature of this conventional finishing process. Also, it is very difficult to control the abrading forces. Okay, so in advanced finishing process, mostly actually these are few of their actually it is controlled. These finishing forces are controlled by external pressure, hydraulic pressure, or magnetic field. So you can control all these finishing forces automatically and externally also. And we can control, precise control of finishing forces are also is possible in advanced finishing process, which is not possible in normal conventional finishing process. Now, requirement of nanometer level surface finish, also it is very much important. Like nowadays, this whatever this missile system, they use mirror or lenses. Actually, they use their surface finish requirement is in the range of nanometer and angstrom level. Mostly, they use actually angstrom level. So for polishing of this kind of angstrom level surface requirement, actually, so this MR fluid, magnetoroidal fluid, is mostly used for polishing this kind of lenses and mirror, which are made of quartz or which are made of glass. Different kinds of glasses are there. So with the different kinds of glasses, they are made of. So for polishing this kind of components, we need actually angstrom level surface finish. So no other conventional process is useful for polishing this kind of workpieces. Now, coming to this different kind of application areas, you can see here. So this is the investment cast mill product, this mill parts here. So this kind of actually this aerofoil structure is there here. You can see. So it is a complex structure. So this component actually can be polished only by abrasive flow finishing process or bacteriological abrasive flow finishing process. Okay, either you can use FA media or you can use MR fluid for polishing this kind of component. So this kind of aerofoil structure also, this is the finished one, this is the unfinished one. Okay, so here this cast aluminum automotive turbo component you can see here. So before finishing it is like this one, and after finishing. So here actually this polishing fluid only we can flow through this intricate surfaces so that you can intricate details actually can be polished by this. So can be polished of this kind of component. Okay, so now this kind of bent tubes, you see here actually this kind of bent tubes. These are used in medical devices. Okay, so medical device valve fittings. So, so tubes and flow meters actually it is used. So even a small amount of actually corrosion inside these bent tubes actually it will damage the whatever this gas flows or liquid flows through this actually tube. So it should be actually impure free. So there should not be any impurities in this kind of actually bent tubes. Now this kind of medical components, medical equipments, so this should be actually nano finish. Okay, so the automatic gear. So we shall discuss later also actually this polishing of these gear, miniature gears, which is used in precision wristwatch. Okay, so for polishing this kind of gear teeth, actually this involute surfaces, whatever the speeds are there, actually this can be polished by this kind of advanced finishing processes or microbiological finishing process. So this is another example of this hard valve. So this kind of small intricate details actually can be it is required to be polished, which is placed inside in our body. So now this kind of automatic components where many holes are there. Actually, you can see many holes and many joints are there. Okay, so wherever actually we make a drill. Okay, so you can see there are small bars are actually generated. So like here you can see here this kind of exhaust manifold. Okay, so here two tubes are actually it is welded together in a third one. So in the welded junction, you can see this kind of fusion zone is there actually there. Heat abated zone and some kind of brittle material will be there in this zone, in that fusion zone. So unless this surface welded zones actually it is polished properly, so there not be actually proper finish or proper flow of fluid through this actually holes. Okay, so here high pressure holes of diesel injector nozzles here. So these holes you can see here actually this at the internal surface of a cylinder itself there is another hole is there. So this whole surface actually it can be polished only by this microbiological finishing process. So there are different other examples are there. So here you can see this is the knee implant. We shall discuss this one later also. Just I am to introduce this one here. Okay, so when actually means old age, actually what happens actually this structure, it is this femoral component in our knee joint. So what happens actually, there are due to the this whatever this fluid is there in between these two bones. So this it dries up. Actually, what happens? It dries up with over age, and then what happens actually? This bone, because of this continuous friction with this one, this tibial component, what happens actually? It wear out, and then whatever these wear particles are there, it further there will be actually two body or three body abrasion will be there, and then it further wears out, and then the person actually old person, it he feels, he or she feels such a lots of pain there. So that's why it has to be removed here, and then one femoral component actually it is replaced, it is placed here. So it is made of titanium alloy or cobalt chromium alloy. So cobalt chromium, it is very costly alloy, actually it is patented one, and otherwise people are using titanium alloy also. And then this is the tibial component here, so it is replaced. And then this so in between actually there is a ultra high molecular weight polymer, actually it is polyethylene. Okay, so this ultra high molecular weight polymer component, it is placed in between this actually this femoral component and this tibial component, and then it is in constant contact with this actually polymer. So always actually this is in nano finish. What happens actually means maybe over time, over a year, what happens? So this uh, due to friction, actually these debris particles in it. So that's why actually this component, it should be highly polished one. Okay. So this kind of freeform surface means you can see here so many. It consists of actually so many surfaces. So one analytical equation cannot be useful here. There are so many patches are there, so many polynomial surfaces are there, and they are patched here. So these kind of components, it is mostly made by this 5-axis CNC machine. So we have fabricated this kind of component, femoral implant. This femoral component we have fabricated by a 5-axis CNC machine, and further it is polished by this magnetogeological fluid using a magnetic field assisted finishing process. Okay, so that's why actually these are the different requirements of this MR fluid, which I'm going to discuss in a couple of minutes. Okay, so now already I've discussed why this requirement. Okay, so so here actually in grinding process, this whatever this abrasive particles, it is in a loosely bonded form. It follows a actually intricate geometries to be finished. Okay, so this in grinding process, whatever these abrasive particles are there, it moves in a actually certain path. Okay, so but for polishing actually for freeform surfaces, complex geometrical surface, we need actually abrasive particles in a loosely bonded form so that it can take the shape of the workpiece to be finished. Okay, so for that actually this FM and abrasive flow finishing, magnetogeological finishing, these are they use actually this polymer media, either viscoelastic media or viscoplastic media, and this kind of media, it can take the shape of the workpieces. Okay, and if we apply magnetic field from outside, and then we can control the finishing process also. Okay, so that's why there are different advanced finishing process. You can see here already we know this is the FM process. There are two pistons you can see here. There are two pistons are there, and this is the finishing zone. Here in this case there is a cylindrical workpiece. So they are polishing a cylindrical workpiece in this zone. They are using a cylindrical workpiece here, and this is the viscoelastic polymeric media here. And Extrude Hone is the company who first developed this kind of media as well as that finishing process. It is very simple. Two pistons are there. So this piston actually they reciprocates, and simultaneously. Means when this upper crystal moves up, then lower crystal also moves up. And in that case, actually, this whatever this media is passes to a restrictive and constrictive zone in where actually finishing is required. So this kind of media, viscoelastic media, which is mixed with these abrasive particles here, it flows through the intricate zones and restrictive zones where we need the finishing process. Okay. So by this kind of reciprocating cycle for sorry, can you hear me?
Yes, sir, you are audible, sir, but slide is not visible.
Okay, okay, sorry.
Connectivity issue, I think.
Okay. You can see here actually this kind of media, viscoelastic media, and the beauty of this media is that actually it is highly viscous and it can take shape of the workpieces. Okay, so means actually if you keep this viscoelastic media in your hand, it will take the shape of your hand immediately. Okay, so any kind of complex surface can be polished by this process. Only thing is that actually this finishing zone here, whatever this finishing zone, that zone has to be designed. Okay, so suppose for the cylindrical workpieces, internal surface, you have to throw the media through the internal surface of the cylinder.
Sorry, sir. Sorry to interrupt you, sir, but slides are not visible. Slides are share. You can re-share, I think.
Okay, so
Slides are now gone. Yes, sir. Now it
it
is
is
visible.
visible.
Visible, very clearly visible.
Okay. So the okay. So now the main problem of this kind of media is that okay, so this main problem of this kind of media is that actually it is very costly. So 1 kg it costs around 4 to 5 lakhs, and the rheology of this media is very difficult to control because this media, suppose if you need to polish for soft material, you need a soft media, and suppose if you want to polish a very hard material like stainless steel, titanium, in that case, you have to increase the content of abrasive particles and you have to increase the viscosity and yield stress of this kind of media. So in that case, actually, it will become very hard and it will remove the surface undulations and it can hold the actually these abrasive particles. Um, so main thing is that like in metal cutting process, tool holder it has to be rigid to hold the actually tool. So in this case, when you are actually talking about this finishing using the uh, bonded these abrasive particles, loosely bonded abrasive particles. So to hold the actually to do the cutting action, these abrasive particles has to be held by some media. So this media actually it is holding the abrasive particles. Okay, so for finishing of very hard materials, in that case, we need actually hard media to hold the this kind of abrasive particles, to hold the reaction force by the abrasive particle. Okay, so same media cannot be used for different kinds of workpieces. So that's why people it means its popularity actually is limited. That's why because same media cannot be used for polishing very for different kinds of workpieces. For workpieces with different hardness, means media rheology cannot be controlled. And the second one is the here this media is very costly. So and also there is a lack of determinism is there. Although this process can be used for polishing any kind of complex deformed surfaces, any kind of complex surface. So now after that actually this MRF process which uses this magnetogeological fluid Center for Optics Manufacturing Rochester University, they developed actually this this meteorological finishing process, which uses MR fluid for polishing purpose. Okay, so here just first I'm going to show actually this how this fluid actually works. This MR fluid. Here you can see these are the circular shape, actually the spherical shape. These are these CIP carbon iron particles. So these are nothing but actually ferromagnetic particles. Okay, so you can see here actually without any magnetic field here, these ferromagnetic particles, these are randomly distributed here. Now, when it comes to the magnetic field zone, what happens actually? These ferromagnetic particles, they form actually these chains. So here, this kind of chains are there. So without these abrasive particles, these chains will be continuous here from north to south pole, and it will be homogeneously distributed. But here, what happens actually in MR polishing fluid? What happens actually? People add abrasive particles also, silicon carbide abrasive particles along with these CIP particles. Okay, so these abrasive particles, these are silicon carbide ceramic abrasive particles are there. So these particles, they cannot means they don't have any magnetic field. When you are applying certain magnetic field, this CIP chains, it will form this CIP ferromagnetic particles will form chains, and wherever these abrasive particles are there, they will stay there, and CIP particles will be surrounded. They will be surrounded by this kind of ferromagnetic particles. Okay, so because of this non-magnetic abrasive particles, these chains are actually not continuous. Wherever there is abrasive particles, these chains breaks, and again these chains form. Okay, so I mean to say that actually these abrasive particles are held by this surrounded this whatever this bonding force what I told there earlier. So this bonding actually is given by these kind of CIP chains. Okay, so bonding to the abrasive particles is provided by this kind of CIP chain. So without any abrasive means magnetic field, these CIPs MR fluid actually it is this homogeneously it is distributed here randomly distributed. But when you are applying magnetic field, these chains are forming. Now, if you want to flow the media through this actually through this restricted zone, through this zone here, so you have to break the chains because whenever you try to flow this media, unless you break the chains, it is very difficult to flow this media through this channel. So first you have to break the chains, and then only you can flow the media. And when chains are broken, then this media can be flown there. Okay. So later we shall show actually there are different zones, yielded zone, unyielded zone, I mean solid coat region, and then yielded region here. Okay, so there are different regions are there. Okay, so that we shall discuss later. So here this base media, you can use water-based media or oil-based media. Water-based like deionized water is used when you are polishing like quartz, or you are polishing this mirror glass. Okay, so these glass materials or quartz, this kind of material where this surfaces actually reacts with water, then you can use this water-based media. Otherwise, when you are polishing this metal, so in that case, actually, you can use oil-based media. So oil base this base media, either water or oil. Oil may be actually paraffin oil, silicon oil, this kind of oils you can use. These are called actually mineral oils, basically. And then you have to mix it for a certain time, and then you have to add iron particles, CIP particles, these ferromagnetic particles. Okay, so you have to mix it again using a stirrer for a certain time. Then for making this MR fluid as a polishing media, you can use actually these abrasive particles. So these abrasive particles and then CIP particles, they should be actually with the same size. So these abrasive particles and these CIP particles, they should be of same size. Okay, so that actually this what we have observed that actually when they are actually of equivalent sizes, then only this finishing activities actually occurs better. So then this VIP particles can hold the abrasive particles very easily and give very good bonding strength to the abrasive particle to remove the surface undulations from the water surface. Now, when this media actually is flown through this actually cylinder, Then what about the surface undulations here? Actually, the surface undulations are removed by these kind of abrasive particles. And just I want to say that here actually these ferromagnetic particles, which is called CIP, carbonyl iron particles, FeCO5. So these carbonyl iron particles, they don't take part into the material involved. Only the abrasive particles actually take part into the material involved. Okay, so so this is the concept here. So this is the North Pole and South Pole here, and in between these magnetic field poles, electromagnet pole, this whatever these workpieces are there has to be polished. So in this case, the internal surface of a cylinder is actually finished in this case. Okay, and so you can see here actually these are the magnetic lines of forces are there. These are the magnetic lines of forces. And these ferromagnetic particles actually they form chain along the magnetic lines of force. So you can see here this MRF process already I have shown. So this is actually it is developed by Center for Optics Manufacturing, Rochester. Okay, so for okay, so this is the slide here. So here actually this finishing can be controlled by this magnetic field outside. Okay, so the stiffness of this media is a function of magnetic field strength. Okay, so here you can see this kind of convex shape actually mirror lens actually it is polished here. So this is the disc. So this disc is actually rotating along this axis. So it is rotating here. And now this actually holder, workpiece holder, it is also rotated in the opposite direction. And at the end of this actually holder, workpiece holder, there is a this kind of convex shape actually this mirror is there, which is attached at the end here. And this is the MR fluid, magnetoroidal polishing fluid here. And magnetic field is applied here while we need the finishing process. In other places, actually, this magnetic field is not applied. So through a nozzle, actually, this magnetic MR fluid actually it is flown and it is rotated. And here in this zone, this MR fluid, so here actually magnetic field is applied. So that's why actually this MR fluid become very stiff in this zone. And when we are rotating here on the stiff zone, this MR fluid actually it is sheared over the surface of the workpiece, and due to shearing actually this entire surface of the workpiece is actually it is polished, and it is rotated about this axis. This workpiece is rotated about the workpiece holder's axis, so that's why actually this entire surface of the workpiece actually it is polished. Now already I discussed this one. Now this MRF process actually it is very beautiful process here. So this is the only process for polishing of these lenses and mirrors, and you can get actually finishing in the angstrom level also. So here this the MR fluid conditioner is there. So this MR fluid conditioner it consists of this MR fluid here, and we need to actually control temperature and pressure, temperature and rheological properties. So that's why you can add if you are using water-based media. If its rheology become very high and its yield stress become very high, so you can add a little bit of this deionized water there, so that its viscosity and yield stress has to be consistent throughout the finishing process. For the entire finishing time, so its viscosity and yield stress has to be controlled, and temperature also has to be controlled. You know this finishing process actually is MR fluid property, yield stress and viscosity. So it depends on temperature also. So there is a peristaltic pump is there. Through this pump, MR fluid is delivered through this delivery nozzle over there. So it is delivered and it forms this kind of actually ribbon here, and then this kind of convex shape workpiece it is placed at the bottom of this workpiece holder, and it rotates about this axis so that entire surface can be polished. And now at different places, so this kind of actually rolling motion is given, so that entire surface of the workpiece can be polished. And after that, actually there is a suction pump here. So this is the suction pump. Through this nozzle, this MR fluid is corrected and taken back through the fluid conditioner with fluid conditioner. So this is the electromagnet. So in electromagnet north and south pole, you can see here this north and south pole, it is made in such a way that fluid is applied only at this point. You are not applying any magnetic field, only it is applied at this point only. So this is the main concept behind this methodological finishing process. You can see here initially this thickness of this fluid, it is very high. So after that, actually when it is sheared, so then so this is the shear thickness after shearing this MR2. So this fluid over the drum, so over the drum actually it flows like this. So here one thing actually I want to say here, whatever this drum is there, actually this you can say this drum. So this is the disc basically. Actually this disc, it is a part of a sphere. So it is like actually this kind of spherical, actually means it is a part of a sphere only. So so this shape actually it is made to make this point contact. Okay, so so here this ribbon, it is a hemispherical ribbon is generated and there is a point contact. So this is the polishing spot, and because of this dwelling motion, this polishing spot actually it is varied over the surface. So for a certain 4-5 seconds it is kept depending on the requirement, and it is shifted by this dwelling motion, and at the same time it is rotated also. This work is rotated over the tool holder, and fluid is actually flown from right to left here you can see. And magnetic field is applied only in this zone where we need to do the finishing action. So this is the piston equation. Using this actually you can calculate material removal rate. So it is pressure and then relative movement, relative velocity between the workpiece and the media. Okay, so this is this setup already I have shown. They have developed different setup. This is the first setup they have developed. Now this work, this MRF actually methodological finishing, that the problem is that it can be used only for flat workpieces. Okay, so for external surface only it is useful, but for internal surface it is very difficult. Convex, concave it is okay, but for external, mostly flat surfaces it is okay. But for internal surface, for complicated surface, complex deformed surface, it cannot be used. Okay, although here actually advantage is that actually finishing you can achieve up to the angstrom level. At angstrom level finishing can be achieved, and finishing forces actually can be controlled. So whatever these magnetic field chains are there, their strength can be controlled by applying external magnetic field. But here only the shape limitations are there. So this is the experimental setup, MRF experimental setup we developed in our lab. So this is the actually this disc you can see here. And instead of electromagnet, actually we have used permanent magnet. So this kind of cylindrical magnet actually we have used. This magnet, it is kept just inside the, it is made of actually perspex workpiece, and at the means inside actually this kind of cylindrical magnet is kept, and now this it is attached over a shaft, and this shaft is actually rotated using a BLDC motor. Okay, so so that is a controller is there. Through this controller you can control the RPM of this actually shaft. And now this is the one stepper motor, another stepper motor is there in that side. Using this two stepper motor, actually this XY table can be moved, and it is attached to a Arduino die, and we can control the path. And now this there is a manual lap jack is there. Using this manual lap jack, this height can be adjusted. Okay, so this setup we have developed for it is equivalent to that. Not exactly equivalent, so it is similar to that methodological finishing experimental setup. It is developed in our lab. So what is done here, using this advantage of this abrasive flow finishing, where any kind of complex surface can be polished, and methodological finishing where advantage is that actually any kind of means we can get surface finish in the angstrom level, and finishing forces can be controlled. And same MR fluid can be used for polishing any kind of workpieces by changing the magnetic field. So by taking this advantage of this both AFM and MRF process, we have developed one process that is called magnetological average finishing process. So in MRF process, it is similar to this MRF AFM. So there is no shape limitation, and also it uses MR flow. Okay, so this is the experimental setup here. You can see these are two coils of this electromagnet, and these are the two core materials of this electromagnet here. And this is the cylinder where you are doing the finishing action. You are applying magnetic field here. These the two cylinders are there. Top cylinder, this is the bottom cylinder. These two cylinders are actually filled up with MR fluid, and this is the finishing zone where we are applying magnetic field. And these are the two actual hydraulic cylinder. So this hydraulic cylinder here, one piston is there, and there is another piston. And now this hydraulic cylinder, it is connected to this hydraulic drive. Okay, so this is the pump here. Okay, so here the specification, actually we have used 100 bar pump. We have purchased this 100 bar this hydraulic unit. So it can pump up to 100 bar here. So this two hydraulic oil, it is connected at the top, at the bottom here. This piston, and here another piston is there. So this piston, it is made of actually Teflon ring. So these two pistons are actually connected by a connecting rod. So when hydraulic oil comes here, it pushes the piston here and it goes down. This piston also, it goes down here, and fluid goes to the this finishing zone. And then this hydraulic piston, this MR fluid piston also, this bottom cylinder, it goes down, and then it is connected to this connecting rod to this hydraulic piston. Then this MR fluid comes returns back to this hydraulic unit. Like that, actually, this kind of reciprocating motion is given. Okay. So this setup, actually, it is developed a similar setup we have developed. We have showed what setup also. Okay, so just I want to show what are the components here. You can see this is the hydraulic unit. So this is the DC power supply here to supply the current to the electromagnet here. And here you can see this is the core material of this electromagnet. Okay. Now it uses actually limit switch, two limit switch, one limit switch is here, another limit switch with this step button. Okay, so to control the changes in the direction of this fluid. Okay, so once it is going down and then again it is going up. So like that, this kind of reciprocating motion is given. Okay, so like that it works. Okay, so this kind of workpiece, flat workpiece you can polish. You can keep this flat workpiece at the internal surface, and you can flow this media, and then whatever these abrasive particles are there, it will remove the surface contamination. And now you can use North pole here, the South pole here, so that a magnetic field will apply across this workpiece. So these are the different kind of fixtures to flow the media to this finishing zone here. So designing of this actually this workpiece fixture and as well as magnet fixture is the thing you have to design for every workpieces. It will not be same for all workpieces. Now this is the electromagnet here. You can see here. So this is the electromagnet. So these are core material here. Core material of this electromagnet. So this it is called actually H-type electromagnet here. So here this kind of pure iron actually used. So in here actually this bright bar cold rolled anneal steel is available, so that can be used. Otherwise, you can purchase pure iron. So here this carbon percentage is very less. Okay. So like that, actually this coil heats up. That's why there is a copper tube is placed over there. So remove the heat. Okay. So now I shall quickly go through this actually how we shall make this actually media. So this is the continuous phase of media. So this continuous phase it consists of water-based media or oil-based media. Then we use magnetic particles there, and we add certain kind of additives also. So these additives actually because these magnetic particles, carbon iron particles, or if you use electrolytic iron particles also, in that case its density is higher than this continuous phase, this base media of water or oil. So there is a sedimentation of magnetic particles are there. To resist the sedimentation of these magnetic particles, what happens actually, some additives like grease you can use, epithet grease you can add, or there are glycerin you can use, or you can use oleic acid. Okay, so in that case actually there is a one more problem is that actually agglomeration of these magnetic particles. So when you are applying magnetic field, these magnetic particles will be agglomerated. Okay, so when it is agglomerated, in that case, if you remove the magnetic field, then there will be bigger chunk of this iron particles. Okay, so it will make a bigger size. So to reduce, to remove, means to reduce that effect, actually what happens, one oleic acid, if you use oleic acid as a surfactant, it will make a layer over the iron particles, and certain coating kind of thing will be there by this oleic acid, and then two adjacent magnetic particles cannot come close together. Okay, so in that case, whatever this magnetic property, diamagnetic property will be reduced little bit, but we can avoid agglomeration of those magnetic particles. Okay. So when you are applying, adding abrasive particles, then it will this MR fluid become magnetodolumical polyethylene fluid. This fluid actually it, looks like this one actually in a plastic container. It is made. It is solid with material. Okay, so already I told this thing. So without magnetic field, these iron particles, CIP particles, ferromagnetic particles, this kind of random structures are there. When you are applying magnetic field in this direction, you can see clearly you can see that this kind of change. So these are the actually microscopic image of this iron particle. And one more property is that actually remnant magnetization is very less in case of this carbon and iron particle. So this carbon, those who are interested to work in this area, okay. So just one thing to mention that. Okay, so if you want to purchase these CRT particles, the BSF is Germany is the company they actually supply these CRT particles. So the main advantage of using this CRT particle is that actually this here you can see this is the hysteresis loop here. Okay, so magnetic field is increased from 0 to 1.75 Tesla, and then it is reduced here. While reducing, it flows this path actually. So it does not flow through the center, it flows through this red line here. Here you can see this remnant magnetization is very less. Okay, so if remnant magnetization is very less, so it is not magnetized. These heavy particles, carbon nanoparticles, after removing this magnetic field, it is not magnetized. It will be demagnetized immediately. Okay, so in that case, actually, whatever this agglomeration problem can be reduced. Okay, now rheological characterized. Okay, so here just one thing I have to show here. So this MR fluid, it consists of actually like 20% CS gets CRT particles, 20% silicon carbide abrasives of 1500 mesh size here. Okay. So now there are capillary diometer is there. This kind of if you want to measure the yield stress and viscosity of this media, this kind of capillary diometers are there. Through this capillary diometer, you just flow this media through this capillary, and you apply this magnetic field over there, and then from volumetric flow rate you can measure the yield stress and viscosity. So this is the relation here. So this is the viscosity can be calculated here from this equation. Here shear stress of the fluid when you are flowing this media through this capillary. So it depends on del P r is the pressure gradient, R is the radius of this capillary, and L is the length. So volumetric flow rate you can calculate, and then from there itself actually you can measure the yield stress and viscosity. Okay, so here what is done here actually this existing setup is used. Okay, so this top cylinder is filled up with this MR fluid, and then through this actually this it is connected to a capillary here, and there is a magnetic field is applied there. So there is a L by D ratio. L is the length of the capillary by your magnetic field, and D is the diameter of this actually capillary. So L by D should be more than 40. Other than that, this kind of parallel plate meter you can use. This is the tool mister which is attached to that, and this is the bottom plate here. So you can see this is the bottom plate which is same here. Anton Par actually is the company who has developed actually this magnetoroidal device to measure the installation viscosity of this MR plate. And you can see here actually this perpendicular to that this magnetic field is applied. So this is the parallel plate. Top plate is the two-wheel master here. It is made sandblasted because it consists of abrasive particles. And here bottom plate, here you can see it is a specially designed aluminum container. So this is the gap between this top and bottom plate. It is the 1 millimeter gap is there. Okay. So there is a 1 millimeter gap is made in between this top and bottom plate, and magnetic field is applied, and there is a 20 millimeter diameter basically here, and a MR fluid is kept over there, and it is sheared. So rotational speed of this tool master or top plate, it is proportional to the shear rate. And when we are applying magnetic field, then fluid will give a resisting torque. This resisting torque is proportional to the yield stress of this fluid. If you plot this thing, actually this kind of points will be there. And now if you join with the different kinds of models, Bignam plastic, Herschel Berkeley, Casimir model, okay, so you can data feed that, and then you know that which one will give you the highest, which one will give the highest R square value actually. So that fits better. Now, so this experimental thing actually I'm just skip here. Just one thing actually I am to show here is uh, here. So you can see here actually without magnetic field what happens. These are the CIP particles, carbon particles, and these are the abrasive particles. So when you are not applying magnetic field, these CIP particles and abrasive particles are randomly distributed. Now this fluid is actually flown here. Now when this abrasive particle is coming to contact with a surface peaks here, okay, so what happens actually this surface peak, it will be removed. It will not be removed because it will rotate over there because there is no bonding force, and it will just rotate and then it will flow over the surface roughness peak. But whenever actually when you are applying magnetic field, these CIP particles are bonded and they are forming chains, and they will give the bonding strength to this abrasive particle. And when this abrasive particle, when it comes to the in front of the surface roughness peaks, it will remove the surface undulations from the roughness peak, and it will cut over there. So without magnetic field, there is no finishing. Okay. Now I told that actually there are different zones of this finishing. So when MR fluid flowing through a cylinder here, so uh, uh, it is actually like this kind of velocity distribution. Here at the center, this is the center of this actually cylinder. Axis symmetric is shown here. Actually, this up to this zone actually there is no shear. Okay, so means MR fluid is not sheared here. So pressure actually it is yield stress is actually maximum here at the wall. So that's why MR fluid is sheared from the wall, and up to this point actually this MR fluid is sheared. So this is the shear zone here actually MR fluid is sheared, whatever the chain structure it is broken, but at the center actually this MR fluid is not broken here. This is called actually plug flow region. Okay, so we need actually this plug flow region up to this wall. Okay, so that actually these abrasive particles can be bonded together, bonded with a very high strength of magnetic field, so that it can remove the surface undulations. But when in this zone it is sheared here, so there is a chances that actually the surface particle will rotate because they have actually less bonding strength. Okay, so other things actually now one more thing is that actually MR fluid it is called actually shear thinning fluid. You can see here actually this is a viscosity plot here. So you can see viscosity actually reduces with increasing shear rate. So if you increase shear rate, this viscosity reduces here. So that's why it is a shear thinning fluid. And this is the shear stress versus shear rate plot here. Okay. So in normal Newtonian fluid, actually, this one actually it starts from the center at the origin actually. But in this case, actually, this plot actually it starts from here. So this is called actually yield stress of this fluid. So this is the yield stress of this fluid. When we apply certain pressure gradient, then only this fluid will flow. Otherwise, this fluid does not flow. But after it flows, then there is a there will be a viscosity. So it is actually plastic viscosity here in this case. Okay. So now, without magnetic field, these CIP particles and average particles, these are randomly distributed. When you are applying magnetic field in this direction, this is the at the center. It is average particles. It is surrounded by CIP particle chains. Just schematically, it is shown. Now we are giving certain amount of shear here. So in this fluid shear, this chains also bends with increasing shear rate. What happens after some time? It breaks actually. When it breaks, then it gets less time to recombine. So that's why uh, uh, it is difficult actually to recombine. So that's why this fluid becomes actually shear thinning fluid. Now, so after that, actually this MRFF I have shown where MRFF is actually reciprocated. But what happens actually, sometimes when you are applying magnetic field, so like in this case here, this function of this MRFF process. So north and south pole, it is placed opposite to each other. Now, only magnetic field is applied in this zone and in this zone. In this zone, actually, magnetic field is less. So it is difficult to get uniform policing across the cylinder surface. So that's why what we did actually we have taken this kind of configuration north-south configuration. We have rotated this magnetic field around the surface of this cylinder so that actually whatever this chain structure you can see CIP chain, MR fluid chain structure. So it is uniformly distributed at the surface of this cylinder. Now it is actually rotated here. So it is reciprocated as well as it is rotated. And we have found this actually this configuration it is far better than other thing, other configuration. So here magnetic lines of force you can see now this magnet assembly it is rotated surrounding this cylindrical workpiece, and now we have done the different experiments there. Okay, so so these are different components. So these are the different components of this zone in this zone here. So this magnet assembly actually it is rotated using a bell drive here. So this is the motor. So there is a VFD variable frequency drive. So it is rotated. And these magnets actually here we have used permanent magnet. This kind of bar magnets we have used. So these are the 4 slots actually. Using these 4 slots in every slot we have used actually 2 magnets. Okay. So this is the experimental setup we have developed in our lab, micro machining lab at IIT Guwahati. Okay. So using this rotation, actually, what we found that so magnetic force actually this other than magnetic force, that is centrifugal forces are there, correlative forces are there. So it is increased. And now here this MRFIT it is rotating in a helical path. So because of this movement of this helical path, more area. So if you consider a single average particles, you can see here actually more area it is covered now. So we have found actually better surface finish. Okay, in this case, and as more area is covered. So now just okay. So I can you can see this actually slide here. So so here you can see these are the cylinders, internal surface of the cylinder. So it is not polished, and here after polishing you can see it is mirror finish surface. So here it is made, this internal surface, it is made by boring action. So these kind of sinusoidal profiles are there. So after polishing, you can see this is around 16 nanometer after polishing, and these kind of process patterns are generated. So these process patterns are actually very useful for holding the soil. Okay, so at the internal surface of this piston cylinder of our automobiles, if you see, it is made by honing process. Similar to that, this kind of process actually, but they use honing stick. We have used actually mud plate. So at the internal surface, it is mirror polish actually. Okay, so you can see here this outer roundness also it is reduced from 5.17 to 3.39. So outer roundness it is called actually circumscribed circle and inscribed circle. So if you see internal surface, although it is shows actually it is circular, but it is not exactly circular. This kind of surface is there. So after finishing, you can see this after garnish actually it is reduced. So work surface, you can see initially these are the initial surface, and after that actually using the RMRO process with 150 RPM, you can see there is a very good surface it is achieved. So 150 RPM in this case was the best RPM, optimum RPM. After increasing this actually rotation speed, whatever this already finished surface it is, again it is then disturbed actually by this abrasive particles. So this the 150 RPM is the optimum RPM. After that, actually, we have developed one setup for polishing actually prosthetic implant. Okay, so you can see we have used this kind of just going to this final tool shape, just different shape actually we have simulated. After that, we found this one is the actually final one. So at the internally this is the actually permanent magnet, cylindrical permanent magnet we have used, and this outer surface actually this is the new metal we have used. This is the new metal here. Okay, so using this outer surface, this new metal. So this new metal it is used actually it is used for sealing purpose. Using new metal, you can see actually whatever this field it is not actually it is concentrated at this point at this point here, and you can see magnetic field intensity plot here. You can see it becomes this kind of actually spherical shape. Means if you apply certain MR fluid here, and it will take this kind of actually spherical shape. So through Maxwell simulation, actually we found this is the optimum shape of this actually tool, polishing tool. And now this polishing tool it is attached to a 4-axis CNC milling machine, which I have shown earlier. Okay. So this the new metal you can see at the internal surface. Actually, we have kept our this permanent magnet, NDFD permanent magnet. So this is neodymium iron boron permanent magnet, and you can see at this center we got actually around 0.4 Tesla magnetic field. So simulation and experimental we got 0.3 Tesla. So 0.3 Tesla it is sufficient. Now this new metal tool actually it is attached to this CNC machine. This tool holder is attached, and now at the bottom actually this mark plate actually it is attached at the bottom. Now after that actually after developing this tool we have done different kinds of tool path, this kind of zigzag pattern or raster pattern or helical tool path also we have used. So we have some preliminary experiment we have done. Here this is the titanium flat workpiece we have polished, and after polishing actually you can see here this is from 1 to micron, so we got 0.01 micron. So before going for this prosthetic implant actually we had used on a same material titanium alloy of grade 5 ND DI6AL4V, so that on grade 5 only we have used. Okay. These are the actually AFM picture, and then surface topography by white light interferometer picture. Okay. So after that, actually, we have used different types of MR fluid we have developed. So two MR fluid actually we have finalized later. Okay, we have found that actually this titanium with this hydrochloric acid and nitric acid, it reacts with the titanium halide. So here actually this acid we have to utilize. Otherwise, actually this as the titanium, it is very hard material. It is very difficult only using by abrasion. Okay, by MRP abrasion. So that's why some chemical reactions also is required. So when you add this hydrochloric acid and nitric acid, okay, so it reacts with this titanium, and then after that, this whatever this reaction product, it can be removed by this abrasive particles very easily. And second one we have used actually hydrogen peroxide. Okay, so these are the two different types of MR2 we have used, and with different their compositions here it is given. Okay, so first one, we have seen actually these very aggressive reactions we have found, and using that actually we found actually it is initial one, and this is the after polishing we found very good surface finish using this MRP type 1, where we have used hydrochloric acid and nitric acid. And then the second one actually we have seen that where you have used actually hydrogen peroxide. In that case, not very good surface finish we have achieved. So from 64.64 micron to we got actually 70 nanometer. Uh, but in earlier case we got only it is actually 10 nanometer only. So for first one actually we got very good surface finish. What we got type 1 and type 2 we got actually a little bit rough surface. But in some cases, actually, where relative motion is required, like prosthetic implant, knee implant, actually we have shown. So in that knee implant, actually we need very good surface finish. So in that case, actually this type 1 can be utilized. And for type 2, actually it can be utilized where osseointegration is required, means muscle development. You are using some implant like dental implant you are using. Their surface finish also required, but muscle growth is also required. So in that case, actually, this the dental implant you can use this hematopoietic of type 2 for polishing purpose. So after that, actually, we have means weightability. We have done weightability test. Okay, so before finishing, and then after finishing for both the surfaces. Okay, so to find out actually this, we found that actually this type 1, this whatever this finished surface using this type 1, it is more hydrophilic.
Sir, sorry to interrupt you.
Yeah.
Your slide is not visible.
Please
Okay.
again say.
Slide is not visible, sir. PPT is not visible. Please again share. Again share your slide, please.
Is it visible now?
Sir, still not visible. I think this is under process.
Okay, again I'm.
Yes, sir. Yes, now visible. Okay, thank you, sir.
Okay. So this tool path actually already I have shown. So this kind of helical tool path and raster design we have shown earlier. So this one also I have discussed. After that, actually, we have used dynamometer for measuring the forces. So, what are the different forces are there? Okay, so just this is the workpiece here you can see. So, this is the workpiece. Just below the workpiece, actually, we have kept our this dynamometer. So, we want to know what are the forces are coming. So, this magnetic force, normal force, shear force, we have calculated. So, these are required actually when you are automating the process. Okay, so how much magnetic field we will put. So for that, actually, we have done this kind of simulation. Okay, so what is the polishing spot diameter also we have used, and then it is very much important polishing spot. So we want to reduce this polishing spot as less actually as possible. Okay, so after that actually we have done some console study, simulation study using single apex particle, how much forces are coming on single apex particle. Here you can see this is the crystalline diameter here, just over there to one fixture is made. Just above the fixture, one workpiece is kept, and this is our actually this tool, novel tool, whatever we have developed here. Okay, so these are different composition we have considered. So using different composition we have done this experiment. Okay, so after that actually this is our main component here, this free-form surface. So this is the knee joint already I discussed earlier. So this knee joint it has to be polished by MR fluid here. Okay, so this it is attached to this fourth axis. One stand is kept just at the right hand side actually to hold it, and it is rotated using this this fourth axis with a very slow RPM. So up to 5 RPM we can go. So we have used a very slow RPM. Okay, so you can see here actually this knee joint here different zones actually it is divided so that we can measure our polishing forces and also we can measure the surface finish in different zones how it is improved because different planes, so many planes are there here. Okay, so we are rotating because actually this tool every time it should be perpendicular to the working surface so that finishing force should be normal to the working surface. Okay, so so that's why actually this knee implant actually it is rotated about this axis actually to the fourth axis so that every time this tool should be actually perpendicular to the working surface. Okay, so by this process actually at enter means in one go actually you can polish this kind of implant here. Okay, so at the different zones actually we have checked actually what is the surface roughness. So after that standard deviation we have measured standard deviation in initial one and in final one. Final one it is reduced further. So that is we got actually very good improvement. So you can see here 170 nanometer, 140 nanometer, 100 nanometer. So we got actually this mirror finish surface. Okay. Okay, so this is the final surface of the workpiece. So it is initial one actually it is made by a 5-axis CNC milling machine, and then this final one it is polished by MR fluid. Okay, so so for performance analysis, as I told actually this this we need to actually we have for performance analysis we have done actually a typology test. Okay, so fast performance analysis is the surface finish using surface profilometer AFM, atomic force microscope, and then optical profilometer we have used for surface finish analysis. And after that, actually we did actually this typological analysis we have done. What we have done here actually this tool we have made. It is made of the same workpiece actually whatever this titanium workpiece is there we have used the same titanium of grade 5 we have this workpiece is used using the same tool actually this pin it is actually using the same tool this pin actually polished so one pin is polished by this MR fluid another pin it is polished by handmade polisher okay so using this MR paper. Now we want to compare this actually these two tools on a pin on disc. So this tool, whatever it is polished by MR fluid and microbiological finishing process, and it is polished by hand polished. So in both the tool actually we compare where actually this wear rate is less. Okay, so we have found that actually using this microbiological MR fluid finished actually this tool, their wear rate is very less. Okay, as compared to hand polished tool. Okay, so at the bottom surface on the disc actually we made of this ultra high molecular weight polyethylene we have used. Actually, and this is the polymer polyethylene which is used in between this tibial and femoral part in between actually this polymer is used. You can see this the wear path nearby this tool. So two types of tool already I told, hand polished and then this time earthquake polished. So with hand polished actually we have seen their volume loss is also more and also wear rate also more. But with earthquake tool, both things are less. So it is difficult actually to do same thing actually on a same polishing on a knee implant. So for that actually specialized setup is required. So that's why we did it on a pin of same material. Okay. Okay. So after that we have checked the ultra high polymer and the molecular whatever this disk is there. So there before we are after we are testing the circular path, we are trace. So the both things actually we have done. And we are satisfied that actually using the smart quick. So this wear track you can see here. So we are satisfied that using the smart quick polish tool, polished works it can sustain wear for a long time. Okay. So after that we have done finishing on a gear using our this setup. You can see here this is our experimental setup here. We have developed RMR setup. This kind of fixture actually this fixture we have developed there. So we kept our this gear inside that fixture and this small miniature gear. So its diameter is around 10 millimeter diameter. And these are the holes actually we kept to flow the media over the gear actually. And using this magnet fixture we have applied magnet tool. Okay. So these are the plates, different plates actually we have that can be polished. Okay. So so here you can see how it works. This media is going through this, actually it is going outside through this hole. Okay. So after polishing actually you can see initial one, then it is final one. So whatever the states are there, marks or scratch marks, it is already removed here. From this case, it is become highly polished surface. So this flat surface, you can see, and this flat surface also it is highly polished. Involute surface also you can see. Okay, so it is polished. So this is the SCM image. Whatever these bars are there, so initial one, whatever these bars it is removed. Here also whatever these bars it is. Whatever bars here, these bars are also it is removed here. So okay, so with this one already I have shown this one actually whatever micro machining activities we are doing in our lab. Okay, already I have discussed this. So now I thank you actually for listening my talk on this manufacturable finishing. I'm sure that actually using it is very simple to make this kind of fluid. Okay, so this fluid is actually very cheap, and this whatever this experimental setup actually we have shown there. This experimental setup we can develop in our workshop also. We can start working using this process. Okay, so we can start publishing also. So it is, I think it is very easy. You can start trying on that. So now I'm stopping here. So if you have any queries, then you can ask me if you have any queries.
Thank you. Thanks a lot. Thank you so much, sir, for being here with us during this technical session. I hope that our participants are going to be quite benefited by your discussion. Thank you so much, sir. Now, participants, you are welcome for your queries. You can ask your query by raising your hand so that I can allow you to unmute yourself. Either you can write your queries directly into the chat box. Okay, so I can read them for our session expert, so he can reply. So here we will take 2 to 3 minute wait, so participant can ask their queries.
Yeah, sure.
Yeah. So participant, now you are welcome. Your queries are welcome. You can ask. Okay, if you have any. Yeah. Okay. As Nilesh is just raising his hand. So okay, Nilesh, I'm just allowing you to unmute yourself. Okay. Now you can unmute. Nilesh, now you can do.
Hello, sir. Good morning.
Good morning, please.
I'm Nilesh Sardeshmukh and I already completed your course of advanced machining processes NPTEL course
Okay.
with the top percentile. And here I have to ask question that for prosthetic implant, uh, which means if we have to refer the material standards, so from where we need to refer that one?
Material standard, actually this ASTM standard is there. Okay,
STM.
so ASTM standard we got for our this knee implant actually we got from ASTM. What exactly surface finish is required. Okay, so suppose somewhere we need actually in micron range, if we are going for actually nanometer range, then it will not help. And we are extra polishing, actually it will not give any benefit for that. Okay, so from that ASTM actually you can get whatever this required surface finish for which implant, dental implant, for this prosthetic, any implant you can get from there itself.
Okay. And one more question. In case of knee implant, there is a continuous movement and therefore friction is there.
Yeah.
As well as in case of hip joint, femoral head bone, uh, there is a wear and wear.
Yeah, that is a
So their finishing required is on the high side, I think.
it is actually finishing requirement is more in both the cases. Okay, so in knee joint as well as that hip joint, whatever this ball is there in hip joint, so there actually finishing requirement is more. So there I have shown actually two types of fluid. So fast fluid actually we found that actually it is giving very good surface finish. Okay, so but second fluid their surface finish is less, but for osteointegration it is good actually where we need actually muscle growth. But where high friction is there, in that case actually surface finish as much as possible.
Okay, okay, sir. Thank you, sir. Thank you, sir, for your guidelines.
Anyone else out of the participant? Either you can raise your hands. We are just waiting here for one more minute, okay? Because the time is already about to over. Okay, I think participants
Okay,
have
then.
already got their responses from your kind discussion throughout. So thank you so much, sir. Thanks a lot for being with us. It was very nice and our pleasure to have you over here. So thanks a lot, sir. Thank you so much.
Thank you again actually for giving me opportunity for your short-term course. Okay then. Okay, thank you. Thank you.
Hello, sir. Hello.
Yeah.
Yes, yes.
One more question for checking the tribological performance
Yeah.
for hip joint and knee joint. So, which type of characterization methods are preferred? Hello, sir. Hello. Is it audible, sir?
You are audible, Nilesh, but I think that before hearing your query, I think he has already gone, means left. So, okay, no problem. We will circulate his email. If you have some queries further, then you can write directly to him. Okay.
Okay, sir.
Now you can unmute. We'll begin our next couple of minutes. We are beginning. Next session will be just begin in couple of minutes.
Yeah. Dr. Ravi, hello. Dr. Ravi, shall we start?
Yes, yes, we can.
Hello. Hello, Dr. Ravi, are you there?
Yes, yes. Am I audible?
Yeah, you're audible. Yeah.
Yes.
Okay. So, dear participants, good morning to all of you. I once again welcome you all in the second session of the day. So, in this session, Dr. Ravi Pratap Singh from NIT Jalandhar is with us. So, he will share his expertise with us. So, first, let me, before inviting him for a talk, let me introduce him first. So, Dr. Ravi Pratap Singh is an assistant professor at NIT Jalandhar, and he has contributed significantly to the development and enhancement in the engineering sciences and technology, particularly in the field of advanced processing of technically superior engineering materials. So, prior to joining this NIT, he has also served the Department of Technical Education, Uttar Pradesh, for 2 years. He has received his Doctor of Philosophy degree in the area of rotary ultrasonic machining for advanced engineering materials and MTech in mechanical engineering with the specialization in industrial production engineering from the NIT Kurukshetra. He is life member of Indian Institution of Industrial Engineering, Mumbai, and Science and Engineering Institute, Los Angeles, USA. So Dr. Singh is also a senior member of Indian Society of Mechanical Engineering, Chennai, India. So he has published more than 65 articles throughout his entire his career in the several SCI Scopus SCI Scopus Index journals, including national and international level conferences. He is also he's having 7 book chapters in his account. His broad area of research are follows: conventional and advanced manufacturing processes, modeling and optimization methods, empirical modeling of operational system, advanced engineering materials, microstructure analysis. He is also academically engaged with the editorship and reviewership with several SCI Scopus Index journal from last 8 to 9 years. He is also the guest editor of World Journal of Engineering, that is the journal by Emerald publisher, and International Journal of Six Sigma and Competitive Advantage Inter Science publisher. So currently there are 2 masters and 3 doctoral research works going on under his supervision. Dr. Singh has organized several national and international conferences at NIT Jalandhar as convener and organized secretary and session coordinator. So now with this, now I would like to invite Dr. Singh to share his words of wisdom with the participants. So now, sir, hand over to you. Sir, welcome.
Thank you so much, Professor Narendra, for this much kind information about me. So I welcome you all again, the dear participant, on this 4th day of the AICTE Atal Academy sponsored FDP. We are organizing at NIT Jalandhar. I am very thankful to the entire organizing team from the Department of Industrial and Production Engineering at NIT Jalandhar for providing me an opportunity to share my research perspectives in the FDP domain with our lovely participants. So I feel pleasured to be here with you all for sharing my views. It's a kind of honor for me. So I'm very thankful to the entire organizing team, NIT Jalandhar administration. So I'm just about to start. Okay, I will share my screen so that I hope that my slides are now visible. Okay. I hope it is visible. So the theme which I have just planned for delivering this talk, earlier I was just looking to share some research perspectives related to the hybrid manufacturing solutions. But what I see that some of the experts have already just gone with that particular content, and I was not found that particular suitable to repeat the same content or some of the the slides or the text in that way. Okay, so I just eliminated that content and just revised my theme again for this sharing in this particular FDP purposes. So I just planned my presentation based on the content like the hybrid machining methods for the hard to machine engineering materials with a micro focus on USM and rotary ultrasonic processes. So this is what I have just planned for this particular talk. Yeah, so these are the contents during I will share which during this talk. I will just share some brief about the machining, the advanced machining methods. What are these methods? We will have a case study over the ultrasonic machining because before moving further with the overview over the hybrid manufacturing solutions, which is the rotary ultrasonic machining, which I worked with. We also worked with also published so many articles in the domain of ultrasonic machining as well. But the basic understanding of this ultrasonic machining is quite necessary in that way, so that the basic philosophy behind the development of rotary ultrasonic machining can be grasped. Okay, so at the last we will have a some brief about the hybrid machining processes. What are those processes? And based on that particular theme, how we develop the rotary ultrasonic process. And at the last, we will discuss some future challenges, opportunities, the future research perspectives, okay, etc. So we will discuss about that. So we will start the discussion with a very basic definitions like the machining processes. Okay, so as you can see from the very first statement that the machining is a kind of a conventional manufacturing approaches through the controlled motion of tool and the work table. Okay, so as you can see from here that I have just given a different format for these two terms like the controlled motions of tool and the work table. Okay, because these are the very issues, or we can say the parameters of uh, utmost important so that the proper and significant machining can be done. Just by saying that a kind of a metal removal, the removal of raw material for the base material, or kind of the removal of the redundant material, it's not fulfilling the definition of machining until and unless we are not having the control over the tool and the work table. Okay, so why this control is necessary? So as we know that from the basic definitions that ultimately our goal to just fulfill the customer requirements. The end customer, until and unless if they are not getting satisfied with the product or the output of your process you are providing to them, these outcomes can be in the form of the accuracy, the dimensional shapes, the surface finish, the quality overall of the product. Okay, so these are the few parameters. Based on this, the product characteristics are just identified. Okay, so at the bottom, the images and the particular image is showing the classifications like we are here discussing about the conventional traditional processes, advanced processes. So it's not part of our so much discussion over here, but as a brief, you can see that the traditional machinings were related like the turning, grinding, the milling, and so many operations can be like there. Okay, there can be some sawing operation can be there. There can be shaping, milling, etc. So many like drilling can be there, conventional drilling, and advanced machining methods. Most of you are just aware with. Okay, so I will discuss a very brief about that in coming slides. Okay, so it's a basic of that. It means that here up to here, the major point is about the control motion of the tool and the workpiece. Okay, so now if we are having this much the ample setups over here, means in the existing industries and existing workshops over around the country, around the globe, then why we are moving towards the advanced manufacturing processes, or even why we are just looking forward for the hybrid processes. Okay, so it means that some are the shortcomings of that, some are the problems with the existing machine setups. It means that, so what are those problems? It is related with the very preciseness, means very precise the operations cannot be achieved, cannot be obtained along with the or by using the traditional existing methods. Why? The main reason is that the basic philosophy, the basic working mechanism of traditional approaches in which the material is going to be removed in the form of macrochips, the bigger chunks of material removal. Okay, so ultimately if it's a piece of our workpiece and we are just now going to remove out the material in the form of a bigger chips like chips. Okay, so it means that these are the chips formations are just coming out this particular workpiece. It means that ultimately if we will just conduct some microscopic analysis, then you will see that the material removal is better in this process, but ultimately the surface quality is not up to the mark. Why? Because for having the quality kind of surfaces, one should have the material removal in the form of atoms, molecules, etc. By having the conventional facts, conventional principles for the material removal processes, one cannot achieve these all the requirements because there are so many reasons. One main reason is to use the force instead of some energy. In traditional processes, what exactly we are doing, that we are applying a certain level of forces through the tool over the workpiece surfaces so that the material can be removed. The second point is about this much of force is going to destroy the overall quality of the surface generated. if you are going to remove the material in such a larger chips, the bigger chunks of material, it means that the very close, or we can say the low tolerance, is very tough to achieve. We cannot have the capacity to generate the complex shapes. So there are so many more reasons. We will discuss those in coming slides, coming discussions. Okay. So there are so many reasons. The main reasons are the the quality of the surface, the low tolerance achievement, the overall the dimensional accuracy, the complexity of the processes of the product of having the complex shapes cannot be generated. Okay, so these all the points, the highlighted points, just given an age to the advanced machining method to came into picture, because the process is like we started with the conventional or traditional processes, we moved up to the next stage. Means earlier we were having the traditional or conventional. Okay, we move up to one level, it is become advanced machining, non-conventional machining, it is also called as non-traditional machining. So many names are given. Okay, and again having some issues, now we are having developed the hybrid machining processes. Okay, so it's a journey. It started with the conventional processes and now reached up to the hybrids. Okay, who knows that what are the coming machines, coming industries are just going to utilize, and how these things are going to be implemented into the industrial scenario. So why today's industries are looking towards advanced machining processes, AMPs. I've just given a name, the advanced machining process over here, AMPs in short. Okay, so why the industries are looking towards these machines, these advanced setups? So many reasons are there. The main reason is about the industries. So ultimately, these setups are being employed or being utilized by our industrial sector related with the manufacturing or production related perspectives. So what exactly the industries are doing, that they are utilizing some typical or very complex kind of materials having a very specific properties, characteristics. So the present setups are not having that much capability to process those advanced materials. The next point is about because of the advances in the precision machine tool and the key machine component like the design, the CNC, the computer numerical control, the tuning fabrication, the capability of machining technology that has been improved dramatically. So there are so many evaluations to be done in that particular way. The second point is about the high precision and ultra precision machining processes are required, so that can have the capability to provide you the accuracy ranging from 10 to 100 nanometers and the material removal rate having the range of 10 to the power minus 4 mmq per second. The main thing is that all of you can see that the value of material removal rate is very less. But here the MRR, or we can say the overall production rate, is not the criteria. The criteria is to achieve the accuracy, the precise machine, low tolerance achievements, the complexity of the product can be achievable. Okay, so there are so many more reasons. That's why we are just highlighting two terms over here, that high precision, ultra precision means having a very close tolerances, so that the most of the accurate product can be designed, can be processed out. They offer quality, reliability for conventional products, but also make possible entire new products, especially when mechatronics, miniaturization, high performance are important. These are the very two important points, the mechatronics and the miniaturization. The most of the machine setups being employed in advanced industries relevant to manufacturing production domain. So they are working in the development, in the production of miniaturized products. Why these miniaturized products are being utilized? Because whatever the setups we are using, whatever the products we are utilizing in our daily life, so what are the component, what are the major ingredients, what are the major elements of those miniaturized products? For example, we are utilizing the mobile phones, we are having the smartwatches on our with us. Okay, we are utilizing the electronic devices, but ultimately these all the devices are going to be produced out utilizing some machining setups. and also the main components and their elements too. So how the miniaturized products or miniaturized elements can be developed using the existing setup. So it means that it's a failure of the existing setups and existing machining processes, so that they cannot develop that much qualitative miniaturized product because of the way of material removal, way of machining they perform. They are capable only to machine the material, the workpiece or the product only by the concepts of applying the forces, the generation of the bunch of what to say, larger chunks of material, the larger chips. So that much amount of material is not available even in the raw form. So how you can allow your existing setup to remove the material in a bigger form? So that's the main reason. So however, the advanced machining processes still offers the high production rates, the high surface finish, complex shapes can easily be created. Overall, if we will see, the cost of the production rate is very less as compared to the conventional. Overall, if we will feel the satisfaction of the customer, tolerances at very low level they can be achievable. So these are the very common statement, not specific, not taken up from my research. So these are the very bookish form of points. You can find these points anywhere. The main question, yeah, exactly. I was discussing about these advanced materials. So what are these materials? These are related with the superalloys, the titanium-based alloys, ceramics, composites, polymers, the natural fiber-based composites, safe memory alloys, nanomaterials. The list is very long. And why industries are just utilizing them? Because of their superior and floatier properties. What are those floatier properties? These are the high strength, hardness, but still they are very difficult to process with the conventional methods. Okay, so it means that but ultimately we should have one candidate so that these all the required materials, employed materials, because they are having a very superior applications in the form of aerospace industries, in the form of the automobile industries, in the form of some manufacturing goods, okay, die making and all. So many applications are there. So we can't ignore them. We can't always found for the alternatives, but still we are having that much good quality of material. So we should go with them. We need to find some suitable candidates so that they can be processed with them, along with the high accuracy, along with the high precision. So by conventional machining, the material removal reduces with an increase in the workpiece hardness. So conventionally, as I've already discussed, that we are going to utilize the forces. Okay, we are just going to employ the forces over the workpiece surface with the support of the tool. The complex shapes can, with a very high accuracy, is desired besides the complexity of the surface to be machined. Okay, so complex shapes also require to be machined out with a very quite high accuracy. So these are the all requirements. So that's the main reason that why the advanced machining process can be looked for. Advanced machining will not having the tool that much have a no need to have a harder tools. Harder tools will not be any more necessary. Tool forces do not increase as the material get harder. Okay, so there's so many like chips formation, low lay pattern. Okay, no direct physical contact between tool and the work pieces. Economical. Overall, the main thing is things are going to be very economical in that way. So the different form of energies directly applied, we are going to employ the energies, whether it's a mechanical energy, whether it can be a chemical energy, thermoelectric energy. Okay, so these are the few energies which we are just going to employ so that the advanced machining formation, the development can be performed. Okay. So it's a typical an overview, so many classifications. I'm not going to at all going to discussing about them in detail, but just having for the namesake, I'm just covering these all so that the basic classifications, those are not from this particular subject domain or just doing their research, so that some briefings can be help them. Okay, so the mechanical classification having the ultrasonic machining, abrasive jet machining, water jet machining, abrasive water jet machining, AWJM, ice jet machining is there, abrasive flow machining. Okay, chemical is there, chemical machining, electrochemical machining, ECM is there. For thermal energy utilization, electrical discharge machining, electron beam machining is there, EBM. ion beam machining is there, laser beam machining is there, plasma arc machining, so many, and even some more researchers are doing a lot of works for adding some more setups in these existing methods. Okay, and the same is doing this happening in the domain of hybridization. Okay, so what we can see that the type of energy we are utilizing at a broad sense, four different form of energies. It's a mechanical one, it's a chemical one, electrochemical one, and thermal one. Okay, so having different their working principle, different energy formations. So that's not part of our discussion. So I'm just skipping this particular figure over here. So it's the purpose was only to learn about the classifications. It's an observations of various advanced machining processes. Means if we talk about the material removal rate, ECM is there. If you are looking to machine some non-metal component like glass, quartz, ceramics, and also you can go for ultrasonic machining, abrasive jet machinings. Okay, the if the micro drilling and sheet cutting weldings are required, so you can look for laser and electron beam. Okay, so printed circuit boards as well as component the component form is required, then chemical machining can be utilized. Okay, so these are the, some capabilities of that. Oh, so it's again that the micro machining drilling applications, these are more capable. If you want to have some clean rapid cuts profile formation, plasma, the cavity sinking and standard hole drilling. So it is recommended to go for the EDM and USM, but still so many limitations are there. As you can see that as we have started with the traditionals, as we now learning about the advanced machining processes. So what we are seeing over here that no machine is perfect, no machining perfect. Okay, is an it is also applicable in our human being life, like no, as we normally use a quote that no one can be perfect. So similarly applied in the domain of machining also, no machine can be perfect, having the advantages in some particular domain, having some limitation its own, having some problems, some limitations. Okay, having some advantages also. Okay, so if I'm just saying over here that you can use for the formation of cavity sinking, you can go for EDM process, USM process, but still at the same time, you cannot machine non-electrically conductive material with the EDM process. So for that particular purpose, you can go for USM process. So it means that some limitations are there, some merits are there. So you have to compromise your work according to that. So again, the limitations, the main limitation is the last one. The non-traditional machining methods which have not been proved commercially so far are the ultrasonic machining, abrasive jet, the chemical machining, EBM, plasma arc machining, etc. It means that in the existing scenario of the industrial perspectives related to the manufacturing domain, what we are seeing that the setups like electrical discharge machining, wire electrical discharge machining. Okay, so somewhere we found the setups like the ECM processes or micro ECM processes are being utilized in some typical industries, but still there is a lot of scope, a lot of work is required to prove themselves so that they can be acceptable at industrial level for the commercialization purposes. Okay, so these are some limitations of that. Means also the setups at the initial cost you will find these are a bit of expensive as compared to the traditional methods. The material removal is very low. The main reason is that we are not going to have the material removal in form of the bigger chunks and not in the form of larger chips. Okay, the main reason we are going to utilize the energy and having the material removal in the form of atoms and molecules. So that's the main reason. So yeah, so I just prepared this slide to show you all that how much capable are the advanced machining process, having some limitations, but still are capable enough to generate the quality kind of surfaces. First example was to drilling an inaccessible hole normal to the wall. Okay, so it's a practical image taken up for some published research articles. Okay, so the second is about the machining of parts with typical intricate features. Okay, so that much of kind of micro machining you can see it is not possible to achieve with the conventional processes. Okay, the drilling of a large number of closely spaced holes, but challenges are there. Means we need to design such tools having that much structure at their bottoms. Okay, so then only the processing of these smart shapes can be achievable. You can see the machining deep holes on a curved surfaces. Traditional machining are not answerable to these questions. Okay, so it's a capability of the advanced machining processes to reply over these queries asked from the industry perspectives. These are the machining at nano, micro, meso levels. So many applications are there. Yeah, so it is up to the brief of that, so that how much capable of our the advanced machining processes are, how much capable of our advanced machining setups are. Okay, so as the micro focus, I just prepared the slide. So before moving for the hybridization of the ultrasonic machining, means which is my research area core, like the rotary ultrasonic machining. First, at least have a brief about the ultrasonic machining, because without having a basic understanding of the ultrasonic machining and its working mechanism, it's very tough for one that to learn the hybridization of that. So the main thing is that the ultrasonic machining is a kind of advanced machining processes which comes in the category of mechanical kind of advanced machining methods. Okay, it is having a capability to process both the electrically conductive and non-conductive materials, preferably those having a low ductility and the hardness superior, means the above the 40 HRC, means the examples of having such properties are inorganic glasses, quartz, ceramics, and all. Okay, so these are the some materials from mm, the non-conductive formations. Okay, lecture ले रहा था बोल दो, है ना? Sorry. So the process came into existence in 1945 when El Balamut was granted for his first patent for the process. USM has been variously termed as ultrasonic drilling, ultrasonic abrasive machining, slurry drilling, the ultrasonic cutting, and all. Okay, so there are some reasons that why these are the names are given for USM process. Some reasons are there. I will discuss the reasons because it's a very good responses for these names. Ultrasonic drilling, we are utilizing the applications in the domain of drilling. Okay, sometimes we also perform machining, cutting. Abrasive machining, we are utilizing the abrasive particles. That's why the name is giving. Slurry drilling means the kind of process which is utilized to perform the drilling by employing the formation of slurry as a media, as a transfer media. Okay, so means that we are going to utilize slurry as a transfer media, as a cutting media. Okay, so before moving further, we should learn about the basic formation of these vibrations. So what are the ultrasonics? Okay, so ultrasonics are the high frequency vibratory waves having the capability to having the range of frequency beyond the 16,000 hertz. Okay, which is beyond the capacity of the human ears. So if we are having that much high frequently linear vibrations, so we can say that these are the vibrations of ultrasonic level. Okay, so these are the high frequency electrical energy is converted into the mechanical vibrations via a transducer, or we can say the booster combination. So which are then transformed to the energy focusing as well as amplifying device called as sonotrode. Sometimes some books write this name as horn. Some papers also write it as horn. Most of the time it is called as horn. So it's a main philosophy. First stage, we will have the high frequency oscillations, high frequency vibrations, and we are now targeting those vibrations with the help of the tool, with the help of the horn towards the tool, so that the tool ultimately can vibrate it. Our purpose is to make the vibrations at this tool so that the bottom of the tool can have the ultrasonic vibrations that ultimately now coming into the contact of the slurry, which is a mixture of abrasive particles plus some contained media. Most of the time we use water. Okay, so having the some different proportions. Okay, so it is a kind of research, so you can find out the concentration and all, so you can do that. So you need to just flow that slurry into the machining zone, which is the area between tool and the workpiece, so that the machining can be performed. So this ultimately having this much of the setup requirements, so we can generate the frequency greater than 16,000 and like 20,000 hertz we usually work with. Okay, so having a very less amplitude like 12 to 15 microns. Okay, so the capacity, the power capacity of these setups are going to be ranged out from 50 to 3 kilowatt, 50 to 3000 watt. Okay, so it's the capacity of that. So how much the requirement of the material removal is there, so you can have at home. So some light setups are there, micro USM setups are there having a low power capacities. So abrasive slurry, it's a mixture of abrasive material like silicon carbide, boron carbide, the diamond crust powders, the alumina, means the aluminum oxide. Okay, so having been suspended into the carrier medium so that the proper mixture can be formed. So it's a mixture is called as a slurry, and at the bottom we are having your workpiece. So it's a better diagram. It's a macro view. Okay, just showing you the machining zone. So what exactly is just happening? Okay, so as we know that in case of ultrasonic machining, two different form of major mechanisms are being involved. One is the hammering, another one is the throwing. So what are those conditions? So it means that you can see it's a present condition of the tool and the workpiece. Okay, it's a present condition. But what was the earlier, means what was the beginning? So earlier we were having the tool something like that. Okay, and somewhere we were having our workpiece like that. Okay, so I think that it is clear for you all, so that some basic understanding can be formed. Okay, so it's a tool. So it's a beauty of the tool for used for ultrasonic machining. So we can have our own tool, own design tool. And how the tool designing can be done? It means that what exactly the shape you are going to produce over the workpiece surface. In USM, the tool is creates a kind of replica over the workpiece surfaces. So what kind of replica? Replica related with the shape given at the bottom of the tool. So whatever and why such philosophy is here, I will discuss. So because the replica is going to be generated out because, for example, okay, so I will just take one example over here so that the basic process is more understandable. And that, for example, if we are just having a cylindrical kind of tool, okay, so most of the time you use such tools for drilling purposes. So when the slurry just come into the contact of that, so the related the suspended abrasive particles beneath the tool will just be vibrated out, thrown out over the workpiece surfaces, and so that the proper hole drilling can be taken up, and by the having the application of the servo mechanism, that constant gap between tool and the workpiece can be maintained. Okay, so that this much of formation like that. So what was the tool? So you are having now inside the workpiece. So this is a hole drilling. Okay. So for example, if it's a top view of your workpiece and you are looking to have a triangular kind of shape over the workpiece, or even you can, it is your wish to have triangular kind of drill. Okay, getting my point? Means, okay, I will try to, sorry, show you, okay, but suppose it's a kind of, yeah, if it's a 3D view of our workpiece, so it's a top view of the surface generated, and here, yeah, exactly. It is the exact shape you want to drill into your workpiece. So now it's up to you that how beautifully you can design your tool. So whatever the shape of tool you want to design with, at least you should have the bottom of the tool in such a way so that the something like that, the triangular shape should be given at the bottom of your tool, because your abrasive particles are going to be thrown out, going to be hammered out over the workpiece surfaces from this bottom of the tool only. Okay, so it is a must requirement of that. So okay, so I hope that the basic phenomena now clear. So it is a localized hammering. So these are the conditions where the size of the abrasive particles is a bit bigger as compared to the gap between bottom of the tool and the top of the workpiece. So it's a top of workpiece now, it's a bottom of the tool now. So now the abrasive particles are of bigger size. Okay, so you can see that now abrasive particles are now being hammered over the workpiece surface. Okay, free impact. Free impact means the throwing operation, throwing mechanism. So your abrasive particles, which are very smaller in shapes, as compared to the gap between tool and the workpiece, so these particles will be thrown out and will reach the workpiece surface and create some cavities. Okay, so that the basic formation over the workpiece surface can be done. Okay, so this is the basic mechanism we deal with. Okay, so this much discussion is sufficient at this level. It's a schematic of USM process. Usually, it is a direct figure taken up from our one of the published work in one good SCI journal. Okay, so we just prepared this figure like a block diagram. Okay, so how exactly the setup it looks like. Slurry tank is there. It is a slurry mixer filled up over here. We are just applying the slurry into the machining zone. Mill stand, the fixture is there. The workpiece surface, it's a top surface. We utilize this application for the drilling purposes. The horn we use, the coupler, which is just propagating these vibrations to the horn, the sonotrode, and the power supply ultimately, and the transducer. Okay, so it's all the major components. Some more elements are there, okay, so that cannot be shown in a particular figure. So these are the major elemental images of ultrasonic process. The detailed USM setup, you can see the practical image provided by Sonic Mill USA. So they use this, they develop such setups at their own. Okay, so we worked with the exact setup. So in the next slide, you can see, I will just represent the major figure. So additional elements, you can see the slurry tank is there, slurry pump is there. The auto pack unit you can see. Okay, so auto pack unit is there. It means that you can control the vibrations, you can control the amplitude over here, turn off, turn on conditions are provided with. The power supply means at what particular capacity you are going to utilize the vibrations. Okay, so if it's it was a 1 kilowatt machine, okay, power supply, so at what particular power rating you are utilizing. So we worked with different values and observed the behavior under the changing environments of the parameters. Okay, the tuning control and so many the components are there. The micrometer assembly you can see. Okay, the converter, the clamps, the horn, the slurry hoses and also. Okay. So that is not so much now already been discussed so time. It's experimental setup. We worked with ultrasonic machining. It's same figure, same setup we use for our work. It's an example while we are just finishing the very typical material composite we formed. We developed that composite. It is a WCCO, means the tungsten carbide and cobalt composite, and we performed the drilling operation. Okay, we designed our own tools. One interesting feature to learn about the ultrasonic tool fabrication is that it was a kind of a limitation, so that the tool weight cannot be more than 9 gram. Okay, because it's a condition of that particular setup that the weight requirements are very less, because that was not very high power capacity setup. So it was a kind of limitation. So we were very careful while designing those tools. Okay, so the weight was the criteria, because if we will use some more weighted tools over the available setup, so ultimately the vibrations get failure. They will not be effectively get transmitted up to the tool through the horn. Okay, because ultrasonic vibration get generated when the resonance is achieved. Okay, so that's the main condition. So ultimately our purpose to create the resonance so that the vibrations at the ultrasonic frequency can be generated. Okay, so it's all about the experimental setup we used. It's about the machining zone. Yeah, again, it's a cause and effect diagram we just performed for our research work. Okay, so it's the factors, so many factors are there, like the tool, the slurry, the workpiece related issues you can see. So we worked with 6 to 7 machining characteristics like material mold rate, the hole over size, out of roundness, conicity, very specific and novel machining characteristics we just studied. Okay, so because in the domain of ultrasonic machining, very rarely been studied so far. So it is the need of that particular time. So we studied that much. The parameters. Okay, this concentration are the major thing in case of slurry formation. Okay, type of abrasives you can vary. You can vary even the grain size. Okay, you can develop something related with the number of effective abrasive particles beneath the tool at any time. Okay, so the overall design development of the tool, what kind of the shape of the tool we are going to develop, what kind of tool it is, means whether it's solid, whether it's hollow. So we did that development in our work. So these are the process parameters. I've already discussed all the parameters in this cause and effect diagram. So the again is that, but we selected that parameters like the cobalt content we varied in our workpiece thickness. So that's the main thing, that how ultrasonic vibrations or we can say the ultrasonic machining exactly are going to behave when we are just varying the thickness of the workpiece. We work with 8 mm, we work with 5 mm, 2 mm, very small, very less thickness. We work with the tool profile. We work the tool material, different types of tool materials we selected out. We worked with the abrasive grade sizes. We worked with different power ratings and all. Okay, so ultimately, power rating also called as the ultrasonic power. So we worked with different levels. It was the parametric setting we utilized, having different levels, 3 mm workpiece, 5 mm. Okay, so these are related with the power rating and all. So it is about the applications of ultrasonic machining. So many applications are there. The hole drilling, die formation, the machining of the graphite electrode for the used for the EDM process. Means what is the tool used for EDM process? Graphite electrodes sometimes we use. So we can machine these electrodes using the USM process. It means that it's a kind of a the repairment, or you can say that sometimes the tool gets dull because of some tool wear, so you can remachine again and again those electrodes. Okay, so having a development of semiconducting materials, having applications in glass, quartz, fluorides, barium, titanium, or so many applications are there. And the grinding of glass, quartz, ceramics can easily be done. Okay, so it's again I was talking about our research material. We worked with the ultrasonic machining while conducting ultrasonic machining. Uh, mm, it was the tungsten carbide and cobalt composite materials. Okay, so to discuss more about the composite material is not at my part, but okay, some of brief definitions I can say over here, that a composite material basically kind of developed material which is a combination of two or more materials that results in a better properties. Okay, so that those of individual components used alone, so it will reflect with the better chemical, physical, mechanical properties, okay, as compared to alone. Okay, alone elemental. Two constituents are reinforced and a matrix. Okay, so the main advantages like the high strength, stiffness, and all, the low density, the combined with low density, okay, so that the better density can be generated. Okay, so that the ultimately what was the case of that these tungsten carbide and cobalt composites, that mm, the overall philosophy of what we can say, that the cemented carbide means WCCO composite, which it consists as a tungsten carbide. W as a embedded phase, means a metal binder phase, and it's a high hardness to combat wear, the significant and sufficient toughness to withstand the interrupted cuts or vibrations occurring during the machining process. Okay, so cobalt is having a good toughness. Okay, so it's mixed with that, so that overall the quality, like the toughness, can also be maintained throughout the tungsten carbide cobalt composite. Okay, because tungsten carbide is having a very poor toughness. Applications were very nice. Means the die casting, the high pressure die casting formations, die and punch manufacturing, the jet nozzles, valve seal rings, so many applications were there. Yeah, so it was the case. I'm just saying, I was saying that the detailed tool drawing we prepared, that we designed that all the dimensions in such a way so that the overall weight criteria get fulfilled. Okay, because our ultimate purpose was to just achieve to have ultrasound vibrations at the tool level. Okay, so we designed, we studied the solid tool as well. We studied the hollow tool. Okay, so all the views are here. The finally fabricated tools, you can see the right side tool, it is shown you as the solid one, and the hollow one is here. Okay, it is hollow, it's solid, so we developed such tools having the weight 9 gram. Responses we studied. Okay, so that's already been discussed. It is about the basics about the what is out of roundness, what is hole over size, what is conicity. So these were the few new parameters we studied. However, commonly we study the common characteristics like the material removal rate, the tool wear and all, the surface toughness. Okay, so that's the main thing. What is hole over size? Whatever the expectation you looking to have the drilling using ultrasonic machining and what exactly you are getting. So that's a difference between both. Uh, the out of roundness means when we just see a created drill hole. Okay, normally by the with the naked eyes we see that the hole is perfectly drilled, the circulation is there, but ultimately when we see some microscopic images we found that the outer periphery of this hole is something kind of this much of behavior. So we found that at most range of this the waviness over the circularity over the surfaces, okay, and the minimum dia of the hole where it is lying. Okay, so it's a difference. Okay, so this is how we can conclude our out of roundness. And the third one is about the conicity, means the taperness. It is about the taperness. You are looking for a cylindrical hole, but ultimately it is providing you the. Okay, so okay, I'm just completing this USM setup so that we can begin the hybrid part. Okay, so the macrostructure analysis we conducted out. So just to study that what exactly is happening. So it's a kind of a mixture of the pull out of the cobalt components and the cemented carbide thing. Uh, when we move further at a 5,000 microscopic magnifications, we found some brittle kind of failure. It is also called as the brittle fracture, okay, because it is showing some sharp images. Some scratch portions, means some grinding kind of phenomena also being observed over the surface when studied at 5,000 magnifications. Okay, some larger chunks also get removed. As you can see, some kind of a cavity formation over the working surfaces. Okay, so it is being observed that the material is get removed in the form of larger and bigger chunks. At the last, you can see the quality of the surface generated. Okay, you can see that how much sharp edges are just formed at the top side of the hole drilled. Okay, so these are the some qualitative images. I just I'm just sharing in this particular slide. Okay, yeah. So limitations of various uh, advanced machining processes have just given an age to the hybrid machining solution. So it's a quote I'm just sharing here. These are the shortcomings, means some errors, some problems were there. So it ultimately given just an age to the development and formation of hybrid machining processes. Okay, so what are those unique and inherent limitations? So we talk about the first section here. All the mechanical advanced machining processes like USM, abrasive jet machining, abrasive flow machining, they require the hardness of the abrasive particles. They are all based on the abrasive and their overall cutting behavior. So ultimately, the hardness of the abrasive particles is required over here. Okay. So and ultimately, the hardness of these abrasives should be more as compared to the workpiece. Okay. So that the actual machining can be performed. And also some mechanical damage is also being observed sometimes, like as I was just showing you some same images, it was observed that some of the micro cracks, the micro formation is there, hardness alterations being observed, but not was in our case we studied, but sometimes in the case of abrasive flow or abrasive water jet cutting, it being found in some good research articles. The thermal related advanced machining setups may impart some thermal damages like heat affected zones, recrystallization, recast layer, the splattered particles, okay, over the unfinished workpiece. So that's the main thing, because what's the reason? Uh, it is only because of the the working mechanism of the electrical discharge machining. So in case of thermal based processes, the material is going to be removed by the concepts of melting and evaporation. Okay. So by the concept of melting and evaporation, when a bulk of material is get melted out into a particular pool of space, formed over the workpiece surfaces, and ultimately simultaneously some more amount of discharges are going to be taken place. So because by the virtue of those discharges, those sparks, that molten metal can get splashed out, splattered over the unfinished materials. There they can be, and after a certain amount of time, they can these splattered molten material particles can become solidified. They can get a kind of recasted over the unfinished materials. Okay, so that's a kind of, again, so that again the post machining operations get become more be needed after the machining process. So the limitation with the electrochemical machining, chemical machining, is that only they can process the chemically reactive materials. Okay. So what we can see, these kind of chemical related processes may induce some chemical damages like intergranular attacks, oxidation, the formation of the oxide layers, corrosion can be there. In some cases, cavitation phenomena also been observed. Okay, so embrittlement, contamination, so many things are there. So because they utilize some kind of etchants, they utilize some kind of electrolytes. Okay, so some limitations are there. So you can see that so many limitations are there. As already I'm just repeating the same code, that no machine can be perfect. Okay, having their own limitations, having their own advantages also. Okay, so however, the hybridizing and advanced machining processes with another advanced machining process, or with the conventional machining or finishing processes, to develop a hybrid machining process enables it to overcome these limitations. Okay, so we will just try to collaborate two or more processes together, not only the processes, their working principles, their energies. Okay, so based on that particular concept, the formation of the hybrid machining processes is just formed. So the basic formation of hybrid machining processes, how it looks like, it's a formation between two processes. So if we will just merge up the concepts from the grinding operation and the electrochemical machining, so we can have the grinding, we can have the hybrid setups like electrochemical grinding. ECG can be there. If we are utilizing the EDM applications from the grinding purposes, we can have electro discharge grinding, EDG. We are now merging up the concepts of electrochemical machining and electro discharge machining. We can have, and also the grinding itself, we can have electrochemical discharge grinding. It's a kind of triplex of formation. Some books, some research articles, you can see it's a kind of triplex formation. Okay, duplex, triplex, you can see two observations, two processes are there, two formation or two form of energies we are utilizing. It's a duplex formation, triplex formation. Okay, if we are just utilizing the concepts of the ultrasonic machining, okay, so we are now having a combination of both. You can see at this corner the ultrasonic assisted electrochemical machining. Sometimes it is also called as ultrasonic machining, UECM. Sometimes, so it's up to you that how you are just reflecting your work. Okay, so some researchers publish their work with different names. Even they give their own names to them processes. Okay, so it's a basic philosophy behind the formation of hybrid processes. Okay. Okay, so before moving further, some practical case studies, some basic definitions related to the hybrid process I need to share, because without having that much the clarity in your mind, that it will be very tough to learn more and more about the hybrid processes and their workings. Okay, so the main concept is behind the development of an hybrid machining processes is to use the combined and mutually enhanced advantages to obtain the 1 plus 1 equal to 3 effect. It means that whatever the process you are utilizing, having some advantages like that, having some their own benefit like that, so ultimately when we use them individually, you will have only one number of output, you will have some one number of output. But when you will just club them, it means that the overall effect is going to be greater than 2, means about 3. Okay, it's a main theme, it's a main principle behind this equation. Okay, so now you are just going to apply this particular principle. Okay, so what these hybrid machining processes are having the capability, they are capable to meet the ultra precision requirements. That's the main thing. We are just discussing this term from the beginning. they are capable enough to produce the ultra precision machining operations. To meet the challenges of extended shapes, means complex shapes, to complex cavities, size requirements, to achieve the enhanced surface quality and tolerance requirements with good productivity, and so many more requirements like the difficult to machine materials can very easily be machined out, processed out. In hybrid machining processes, the processes or the energy sources should interact more or less in same machining zone. So these are some typical conditions for that. Then only they are called as hybrid machining processes. The energy or the processes should interact with each other into the same machining zone. It should not be like that you are just merging them and they are just not collaborating themselves over a particular given area of machining. Okay, so this intensifies that the machining operations and results into the low tool wear. Okay, the better surface quality, integrity, the better product quality. Oh, okay, so ultimately we found that overall efficiency of the process is enhanced. Okay, so it's all about that. For example, we just now for so many research work being carried out in the domain of electrochemical discharge machining, we are now capable enough to machine the non-conductive materials also. Okay, earlier it was the limitation of electrical energy based methods like EDM, ECM, that only the chemical reactive or some electrically conductive material can be finished out. But now even we can machine the non-conductive materials also. Okay, it means that now they are capable to process electrically conductive as well as the non-conductive materials, having and also their productivity now just increased by the timings of 5 to 50 times greater productivity. Okay, so that's the beauty of hybridization. The applications are very wider. The initial developments of the individual hybrid machining processes were material, shape, and application specific. However, the hybrid machining processes may in general to be used for a wide variety of applications. Okay, so many applications can be there. The surface quality from ranging from the value of 0.5 microns, good surface integrity, the stress-free surfaces. From the last point, you can see they are also capable enough to generate the ultra precision machining. Okay, the surface toughness from the values of 1 nanometer, tolerances up to 10 nanometer. So very closer tolerances can be achievable. The formation of nano micro size components, 3D micro features, micro holes, cavities. Okay, and also not over the formation over the common kind of materials, over the advanced and difficult to machine materials. Okay, so it's a capability of that. How we can design? What are the design principles and methodologies? Okay, so the aim of designing the hybrid machining processes and related technologies is twofold. Means so many are different, their own concepts are there. The first, it can shorten the existing process chains. It means that whatever the process concepts we are just having at our own, so what we can see that we can shorten the existing process setups. Okay, so we can see that whatever the existing flow of the processes are, so we can modify them, we can shorten them. So it's also be considered by the concepts of the hybrid machining formations, the design principles. The second, it can combine the process capabilities. It means that one process is capable to do something, another one is having capability to perform a kind of some different operation or different capabilities. So those capabilities can be merged up to realize the complex product or to obtain the contradictory machining performances. Okay, so whenever we deal with the machining operations, sometimes most of the time we use two terms, that the material removal rate as well as the surface toughness. Okay, or sometimes we found that material removal rate and tool wear age, we always want to have higher material removal rate, we always want to have low level of surface toughness, always we want to have high level of material removal rate, always we look for lesser value of tool wear rate. It's a common thing. It means that why the concept of hybrid machining processes, the contradictory means these are the combination of contradiction, means because in a common operation it is not possible to obtain both the conditions at one time. Okay, for example, in case of traditional processes, if we are just going to perform a normal turning operation at high feed, high depth of cut, your tool is going to be worn out very easily, very frequently, and at that particular time the material removal is going to be very superior. Okay, so it means that the tool wear is there, but it is at the cost of higher material removal rate. Okay, the second example is related to the some grinding operation, some drilling operation, you can say. Okay, so you can vary the parameter, you can have the higher one parameter, but ultimately you need to suffer, you have to suffer, I must say, you have to suffer your second value. Okay, so these are the parameters when we combine two or more energies. So what we can say, for example, so when it's a case of ECDM process, I need to share that so in where your the EDM process is just now working, the tool is just creating such discharges over there, okay, by having the closed circuit, so that so many discharges are there, the machining is just taking place. So when your capacitor is now just charging itself, so in that particular time, the ECM is just performing the machining. Okay, ECM is now having electrochemical machining operations. Okay, so in that particular time, the time, or we can say the overall the duty cycle is now being efficiented. Okay, so ultimately what is just happening, that overall the material is going to be machined out by the concept of ECM and EDM, and ultimately the tool wear is now going to be lesser because a given amount of material is going to be removed out completely, and your tool wear is now is very less. Okay, so just a minute, just a minute. Yeah, so sorry for disturbances. Yeah. So we were discussing about the basic principles of the hybrid machining formations. You can see that there can be some principles, some design methodology to be adapted out when to develop a hybrid machining processes. Okay. So there are four different principles, at least the developer, the investigator in that particular domain should follow one or more principles so that it can be claimed that the development of hybrid machining process is done. So ultimately, the broadening existence of the existing material processing window of the process, like the machinable materials, means we need to broaden the capabilities. Okay, so ultimately, if some processes are having the existing process capabilities, we need to improve them. We should improve them so that ultimately the surface integrity, tool life can be enhanced out. Fulfilling two contrary machining objectives, we were discussing about that. Okay, the contradictory parameters we were discussing, the gaining the significant benefits of interaction of different process energies. Okay, so different form of energies we are going to utilize. So that's a formation, that's a clubbing together these energies is called as hybrid formation. So it is how the overall design methodology should be adopted. The description, it means that it should be described that what are the limitations of the existing processes. Okay, so if it is limitations, if the limitations are already arrived, then we can say that what are the explanations, means why do the limitation existing, what's the problem in that. If it is possible to modify the existing thing, we can provide the solution into the limit of the limitations, so it can be resolved at this stage. If the third stage, it is how to break the limits. Okay, so if it is possible to break the limit utilizing the hybrid concept, so it can be done. Okay, so these limits can be broken up and the solution to the existing limitations can be provided so that the formation of the hybrid processes can be achievable. So it's a simple flow kind of thing. You can see the diagnosis of that. Reduction means the abstract formation, and here the synthesis. Okay, so synthesis means the transformation of third stage 1, third stage 2. So it's abstract solution, the problem solution. So it's a first step. Why it is the first step? We can't claim the solution over here until unless we conducted the verification. Okay, it's a specific solution. So after conducting the verification, we can claim that the solution is now arrived. So these are the few more elements for designing the hybrid machinings, the knowledge of the limitations of the individual processes. So it's not only necessary to have the knowledge about the advantages only, also the knowledge of limitations. Okay, the design of dedicated machine tools, the technological compatibilities of two process energies, the knowledge of process material interaction, the knowledge of capabilities of individual processes, the interaction of two processes. So many elements, means by considering these elements, we can develop a hybrid process. Yeah. So it is another micro focus over the hybrid machines we deal with. We publish several research articles in this particular domain. Rotary ultrasonic machining, it's a hybrid machining, it's a hybrid manufacturing processes derived into the domain of mechanical energy formation. Okay, we are now clubbing the energies. We are now clubbing the concepts of static ultrasonic machining, simple USM we discussed earlier, USM, which is also called as static. Okay, and also the conventional grinding concepts. So why these conventional grinding concepts are just into the picture, means we are now having a tool having the crushed form of diamond particles at the top of the lower top of the work the design tool. Okay, so it means that the bottom of the tool is now impregnated with the crushed form of diamond. Okay, having the different grain structure, different grain sizes. What does the formation of these clubbed energies will do? They will allow the formation, they will allow the removal of the workpiece material into the form of microchippings and grinding action. Okay, so the concept get patented out, being developed out by Mr. Percy Legge in 1964 at United Kingdom Atomic Energy Authority. However, the original suggestion, if we talk about, it is given by Mr. Brown in 1960. It was proposed and patented out by him. He conducted out the concepts of merging drilling and ultrasonic vibrations. He just giving the idea that these vibrations can be clubbed for the purpose of merging drilling. Okay, so in case of rotary ultrasonic process, a coat will basically be used for the effective flow of coolant. We are not going to utilize the abrasive over here. We will use rather the coolant. Okay, so that particular coolant flow is continuously required, continuously needed to just the washes away the swab, preventing the overheating, jamming of the drill, and keeps it cool. Okay, So that's the main figure. They're taken up directly from the published images in 1964. First, RUM means rotary ultrasonic machining model developed by P. Legge. Okay, so you can see that he utilizes the forged chuck we usually use in our common lathe machines. So to just as a fixer to just so that the workpiece can be hauled out. Okay, so it is just because at the bottom the motor is there, so by the virtue of that motor the workpiece can be rotated out. Okay, so that it was the approach that's applied in some 90s, sorry, 1960s. Okay, so that's the main reason. So we will see, I will just show you that how this modification taken up and how the advanced nowadays how exactly the rotary setups are now working. Okay, the mechanism of material removal is about the concept of hammering action, it is about the abrasion action, and also about the extraction action. So if your indentation and crushing of the workpiece beneath the tool impacted only because of the ultrasonic vibration, if we talk about uh, if you say that the material, most of the material is going to be removed out by the concept of ultrasonic vibrations, it will be called as hammering action. If you will see that most of the vibrations are not being affected and the most of the material is going to be removed out by the concept of diamond tool only. So it will be considered as the removal of material by the concept of abrasive action. And some conditions can be there where the simultaneous action of both means the ultrasonic vibrations as well as the diamond tool is there. Okay, means rotational motion of the tool. So mix up of that, it will be called as extraction action. Okay, so these are the mechanisms. Uh, so you can see from the first image, you can see only the vibrations are there. They are more effective. Okay, you can see the hammering is there. So only the here the vibrations are there, rotation also there, tool rotation is there, so extraction action. And simply if the rotation means it is showing you the circulation of the tool, so it's abrasion, means in this case the most more dominant is grinding action. Okay, so it's a common thing is that. So tool common view is just now shown in this particular figure. You can see the hollow tool. So these are the images from uh, the diamond abrasives. You can see the layered out over the bottom of the tool. Okay, you can see these are the vibrations provided to the tool. Okay, so the concept of providing the vibration is similar. We are just having the transducer, okay, at the top, and we are having the motor so that the spindle of this core drill tool can allow the rotation up to the thousands of RPM. So it's a basic elements of rotary ultrasonic machining process. Okay, so it's a direct image taken up from our one of the published article. Uh, the ultrasonic transducer is there, electrical motor being utilized. So it is ultimately the ultrasonic spindle. Okay, it's a horn and also the development form and the designing of the tool. Okay, so it's a common thing is there. So many more ultrasonic related common the feature we incorporated into the development of the setup. Okay, so these are the related parameter to that only. So it's a main diagram you can see. Okay, so these are the images directly from the live image from the work set we employed with. Okay, so these are the ultrasonic transducers. It's a combination of that, the fixer. Okay, so these are the diamond abrasive hollow tools. Okay, it's a large view of that. So it's a alumina particle we are now machining with. Okay, so we work with the different form of the advanced ceramic material. So it's the alumina ceramic workpiece. Okay, so it's a metal bonded diamond core drilling is just showing you. Then again, the kind of the cause and effect formation, different form of the tool can be developed. So many parameters can affect the process overall. The tool inner outer diameter, concentration, the abrasive size, bond type, what kind of bond is there. Some researchers developed their tool by the metal bonding materials. Some utilize the polymeric kind of the joints, ceramic based joints utilized. Okay, so great number of the uh, abrasive particle utilized. Okay, so abrasive is used at the diamond because you can develop their own setups also. We work with the diamond tool to crest form the right angle face tempered. Okay, so the machining components are similar with the USM process normally we use. The coolant kind means type of coolant you are using, the concentration of that, continuous, intermittent, okay, pressure, at what pressure you are using, the flow rate provided, okay. So these are again the similar parameter. We worked with the material movement rate, chipping size, roughness, chipping thickness, and all, okay. Primarily we studied the major parameters, the feed rate, spindle speed, the torsionic power, coolant pressure. It's a diagram from the past studies. So far, the most of the work carried out in the domain of surface roughness, cutting forces. So these are some common studies. So that's why we worked with some the penetration rates. We worked over the chipping thickness, chipping sizes. Okay. The material we see that most of the materials the machine with like the different the ceramics, the advanced ceramic, zirconia, alumina, and all. Very rarely studied some biomedical applications. We worked the two that biomedical ceramics we studied with. The quartz, the rarely been seen the quartz as a work material. We studied with that, the optical cane and glass. Okay, so many materials being studied. The specific geometry we talk about. Okay, so you can see that that's a kind of, you can say, the limitation of that, so that once the whole formation is now carried out, so once our tool reaches at the bottom of the tool, okay, so because of the brittle nature of these materials, means this advanced ceramics, the lowest layer of these advanced the ceramics is not capable enough to hold up the stress at this particular level. The stress is very high. It means that the lowest portion of that the working plates of the ceramics now sticked with that particular machine rod and just fall down into the machining zone. Okay, so we need to recollect that, so that the study for this particular the chipping size, thickness, and dia can be conducted out. Okay, so that's the main thing. So that's the kind of limitation also, but overall quality of the surface generated is very superior, very extraordinary surface produced. Okay, it's a different tools we used. These are the chamfer tool. You can see some. Okay, so it's one of the diagram practical images. The tuning length, you can see it's the metal bonded diamond abrasive particles tool connection portion, you can see. Okay, so it's you can see here the 220. It's just placed in opposite direction. However, you can see the 220. So it's a tool having a grid size. Okay, at this 220 level. Okay, so the problems reported. Okay, so it was the main reason why we worked with this setup. So many reasons were there. So it's not required because it's time constraint to detail out all the reasons. But commonly I can say that so many reasons were there that the existing setups, whether it's a traditional or the advanced setups are there, but having their own limitations, they are not capable enough to have some geometrical related inaccuracies, heat affected zones, conicity, out of roundness. We work with the USM process also, so we are also the observer of those limitations. So how we can claim that's not having any limitations? So we work with that particular setup. So in the conicity lack of issues or out of roundness already been observed. So it was a difficulty doing that. The quartz material we worked with, it has been observed from literature that different machining processes being employed for the fabrication of for the production processing these quartz ceramics. Okay, so again the problem is like surface defects, larger cutting forces, the formation of precast layer and all. Okay, they are not capable enough. The machining of Macos ceramic, it's a beauty of our work. It was the novel material we just the machined out for the biomedical the application purposes. It's a kind of dental ceramics, and we machine this particular material. Okay, so very less studies reported so far in that particular way. So however, some of the traditional machining connected out, like the turning and all. So it was reported that microcrust formation, the very less accuracy, dimensional problems were there. Okay, thermal, it was the limitation of the thermal related processes like EDM, wire EDM and all, so that the electrically conductive material, they are the ceramic material, non-conductive kind of. Okay, so these are the main reasons. The more beautiful the point is about the RUSM process is about it's a process overall developed, and it's a non-thermal, non-chemical, non-electrical man. And creates no effect over the environment. It's a completely environment friendly kind of, and also the coolant use is not going to be so much harm, not any harm for the social structure as well as the environment. So these are the few problems. Sorry, these are the few important points about the rotary ultrasonic machining. Okay, so in short, I'm just briefing out these all the merits. Okay, so many points are there, and also you can see the research articles have been published. So most of the details are taken up directly from there. Okay, so it is about that. So the rotary ultrasonic machining is one of the cost-effective and environment-friendly process you can see for the machining of advanced engineering ceramics with improved hole accuracy, superior finish, uh, uh, tight tolerances can be achieved. Okay, so it's all about that. Yeah, so it is about some the material we studied. Okay, so the alumina ceramic we studied that material. So applications are very superior abrasive material. In the form of abrasive material we use spark plug development, the wear pads, and the development of seal rings, furnaces. Okay, so it's all about that. Al2A3, it's a formation chemical formula of that. Okay. The photographic view of machined alumina ceramic. Okay, so photographic view means that what exactly we conducted. Okay, so we performed the rotary ultrasonic machining of that. Okay, so it's you can see from the left image. Okay, so it's a machined component. One of the view is there. So and the second side you can see right side the edge chipping is now try to show you. The chipping diameter can be seen. Okay, so very clearly visible that how much less it is. It is not so much at higher side. Okay, and you can see beautifully that how much clear and close holes can be developed. That's the beauty of this setup. Okay, these are the very brittle components. Okay, so these are the quality of the holes you can see. Second is about the quartz ceramic having superior and excellent applications in the domain of the sensor formation, filters, the pacemakers. Some component of that getting formed with the quartz ceramic, electronic resonators, foundation. Okay, so you can see it's a disc we use for that particular purpose. It was the most brittle material out of these studied the ceramic plates. Okay, so the top surface is very clear. Okay, so whatever the some inaccuracies or some the formation of the chipping you are seeing over here, it is not at the top side, it is at the bottom side. Okay, because of the transparency of the material, they are looking like that they are at the top side. Okay, so they are at the bottom side of that. So you can see the edge chipping diameter, chipping size. Okay, so it's a disc, and you can see that because still uh, after the available after the existing the brittleness of the material, you can see that how beautifully the closed holes can be formed. Okay, so that's why the kind of a study check out the machinability of the quartz material. The Macor ceramic is a kind of a biomaterial. It's a technically advanced ceramics having a the beautiful combination of 45% of borosilicate glass and 55% of fluoroplugopite mica. So that's a Macos PLS structure because of the form the ingredient like mica into that. Okay, so that's a beautiful structure. The welding nozzles, then see the medical components, the major applications of Macos ceramic. You can see the images again, the similar images. You can see the quality of surfaces, hole drilled. So it's very beautifully machined material having a very qualitative surfaces. So these are the few. It's not so much relevant over here. These are some statistical analysis we conducted out. You can see the behavior and all. Okay, so that's not so much important by the perspective of hybrid machining over here. But we found that most of the time the speed rate as well as the stuff, the spindle speed found as more significant in every cases. So, these are again the results of the chipping thickness. Okay, so these are the macrostructure analysis and the results derived. Okay, directly you can see the abrasion remarks over the machine surfaces. Some these are the formation because of the grinding action taken up. Okay, some void regions also been observed. The some along with the plastically deformed regions, some sharper edges also showing. So it was the claim that the machining is having capability to remove the material in the by the principles of the ductile failure as well as the brittle kind of failure. Okay, so some ductile flow regions also there. You can see the plastic behavior of the material being removed, the grain pulled out regions. So at some higher feed rates, you can see the some damaged or depleted images. Okay, so you can see these images. Okay, so these are the damaged images. Okay, some sharp regions also been observed. So these are the some uh, the evidence is for the brittle failure. Okay, so you can see the edge quality, means it's a ultimate image quality, means edge quality at the top side of the whole drill. Okay, it's these are the images directly from the alumina particles. Okay, alumina particles, you can see these are the images for the chipping size and chipping thickness for the alumina particles. You can see I'm just quoted out a short abbreviated term like RUMAC, means rotary ultrasonic machining of alumina composite, sorry, ceramic. Okay, it's RUMQC, means rotary ultrasonic machining of quartz ceramic. Okay, so again, the deeper groove mark is just showing you that, as I have already told you, that because of the brittle nature of the quartz ceramic, so most of the bigger chunks you will see in the microscopic images. So we found the most of the material removal only in case of quartz ceramic. Okay, so these are the few images again showing you the bigger chunks and along with the deeper indentation marks. So that because of the okay, so some partial ductile flow regions also been observed. Okay, so it is the cases where the spindle rate speed was very high. Okay, so these were the regions where we found some mixture of both the concepts. So again, the fracture regions being observed. Okay, the high brittle fracture, so it is at the high feed rate levels. So these are the some images, left side images showing you the bottom side of the drilled hole. So it is showing you the chipping size, okay, edge chipping, how exactly it is happening, at what level, and you can see the sharp edge at the entry side. Again, the same images like that for the cone. So they are the images for the Macor ceramic at rotary ultrasonic machining of Macor ceramic. So again, the images like that. So these are okay. The similar behavior we observed. Some specific region are there that the because of the involvement of the mica flex into the development of this ceramic, so that they directly get removed because of the nature of the mica. Okay, so deep penetration was also observed, and some wear out region of the mica flakes and brittle fracture regions also being observed. So it is the quality of the surface. You can see that we also created some blind holes, we also created some through holes. Okay, so overall the ultimate quality we observed. So it just ultimately show the beautifulness, means the what a hybrid method, what a hybrid process can do. So it is again as per the content of my the discussion. Just I need to discuss some future research perspectives also in the domain of rotary ultrasonic machining. The development of some overall robot system design can be done. Some very rarely been improved, rarely been observed that very less advanced machining, advanced optimization method being observed to optimize the some MATLAB based tool can be used. Some okay, some model can be formed over some simulation and fuzzy tool based validation can also be employed. Drill hole accuracy and integrity we can work over there. Some of the researchers are doing at here at NIT Jalandhar under our supervision. They are developing their own setups. Okay, so at NIT Jalandhar we are still working to develop more and more setups in to develop more hybrid setups. Okay, our masters, our doctorate students are working day and night to develop more and more setups, so that they are working their designing concept, their fabrication. Okay, so that the accuracy cannot get suffered at all. Okay, the machining at micro level. Okay, so once we deal with the macro level machinings, okay, so it's in also the major portion which cannot be ignored at all. It's a micro machining, as in the beginning I was just saying about the miniaturization, the concept of miniaturization and why it is needed. So it's all about that. So without having the micro setups, the formation and the development of sub product cannot be done. Okay, so some more like the machining of hard and tough composites. Okay, so still some questions are there which are to be answered by these development of hybrid setups. Okay, so many queries, responses and answers being asked from these hybrid machining setups. Okay, so they are there to answer everything, and in coming time it's a very bright future for these all the hybrid machining components being developed so far. In some additional research areas, you can see the density of the work material. Like in case of composite materials, we use some sintered parts, so that overall density and its variation can be observed, that how beautifully it affects the machining performances, the torque generated, how exactly the cutting temperature is just forming during the machining. Okay, so some, apart from some technical or some machining like of responses, some environmental related machining based issues can also be studied, like the handling of cutting fluids, so that the overall the environment cannot get affected. Noise control, because it's ultrasonic processes, so one of the limitation, that is some noise being generated, because these are the ultrasonic vibrations, so these are very high in frequency as well as in noise also. Okay, so along with the frequency, the noise is very high. The microchips management, so whatever the microchips during the concept of ultrasonic machining we are using, so microchips, how to manage them, how to treat them, so that they can be very easy to dispose of into the environment. Okay, so that's about that. Yeah, thank you. Your queries are welcome. So it is done from my side. Okay, so it was done. It is completed. Thank you. So whatever the queries are there, you can ask. Okay, so it was the discussion over. Your queries are there. Your queries are welcome. I'm waiting for the queries. Okay, so you can ask queries. So Dr. Naren, it is done from my side. Am I audible?
Dear participants, if there are any query, then you can directly ask to Professor Ravi. Sir, one query from Manoj Kumar. Minimum possible diameter by RUM.
It is very nice question asked by Yeah, I got your query. It is nice query asked by Manoj. Thank you for your query. Uh, it is a kind of discussion where the kind of material which is under the process is also very important. Okay, so when we deal with the micro kind of a formation, okay, so whatever the work we conducted out, we developed the setup, we work with the setup to form the diameter ranging from uh, 3 to 6 mm. Okay, so it was the capability we developed. Uh, it is at the end of the formation. Okay, so if accurately you can do that because you need to provide the passage for the effective flow of the coolant also. Because without having that much passage, you cannot ensure that overall swarf removal and the heat management can be done in case of rotary hybrid ultrasonic machining. Okay, so if it is manageable, then you can go, you can try by the micro tool formation ranging from a bit of a 0.8 mm to 1.5 mm also. Okay, I hope so because I have just observed, I have just reviewed so many research articles in that particular way, so that some researchers are around in countries, the name cannot be, I cannot reveal their names because it's a confidential, but they are working some micro tools. They are forming some micro tools having the ranging, whatever I'm just sharing over here. So I hope that you got your answer.
Thank you, sir. If there are any query, then you can write on chat box or directly unmute yourself, and you can directly ask to Dr. Ravi. If there are any query. Sir, I think there is no query. Either we can conclude the session, and our next session will start at 2:30, sharp 2:30, and hope, we will meet on 2:30.
Okay, thank you so much, dear Madhusudan. Thank you. It was my pleasure to share my research perspectives with you all. Okay, so we meet again with our next session at 2:30. Okay, so that all the participants, we are very highly thankful to you, all of you. So being patient throughout all the sessions. So the last session of today's will just held at 2:30 sharp. Okay, so be there, have your break. So okay, take care. Bye bye.
Thank you, sir. Thank you, sir.
Thank you so much. Thank you.
Dr. Ravi, am I audible?
Yes, Professor Narendra, you are completely audible and voice is very clear.
Thank you so much, sir.
Okay, so we are just waiting for more participants to join. Okay, so in couple of minutes we will begin the session. Yeah, so very good afternoon, you all. So it is the last session of today's, and it's a post-lunch session, and we have our session experts for this particular session. Professor Narendra Kumar has already joined us. Before requesting Professor Kumar for giving his talk, I would like to share some brief about him with our participants. Professor Kumar is working in the Department of Industrial and Information Engineering at National Institute of Technology, Jalandhar. He obtained his doctorate degree in the domain of mechanical engineering from IIITDM Jabalpur. His broad area of research is related with the development and performance evaluation of pellet-based additive manufacturing processes for flexible parts. His thesis project was a part of a Department of Science and Technology sponsored project entitled as Hybrid Additive Subtractive Manufacturing Systems using CNC Machining Center. Prior to joining IIT Jalandhar, he has also worked for the Institute of Technology in Wardha, Maharashtra. He also worked on a DST sponsored project entitled Development of Metal Based Deposition System using Induction Heating Method as research associate. His research interests are broadly related to additive manufacturing machining methods, and developments. He has published about 30 plus articles in various international and national journals and international conferences. So there is so more points to be shared about Professor Kumar, but because of the time constraint, I would like to extend my request to Professor Kumar to share his research perspectives with you all. So, Professor Kumar, now it is hand over to you. We welcome you, sir.
Thank you so much, Dr. Ravi. So, dear participants, I welcome you all in this session in which I am going to cover the hybrid additive subtractive manufacturing related topics. So, first of all, I am really thankful to the organizer of this course to invite me for this particular expert talk. So, now I would start with the additive manufacturing. Okay. Then after we will see some of the steps in additive manufacturing, and then I will move toward the hybrid additive subtractive manufacturing processes. So now let me share my screen with all of you, and then we will start discussion on the topic. So I hope my screen is visible to all. the participants?
Yes, yes, it is completely visible and very clear.
So the specific topic of the today technical talk is retrofitment on CNC machining center for additive manufacturing. So I think this topic is really suitable for this particular course because the course title is Hybrid Machining Solution for Complex and Typical Engineering Applications. So we will see some of the applications where hybrid approach can be useful. Okay, so today we will see how hybrid approach can be useful in the area of additive manufacturing, right? So these are my presentation outlines. So I am going to cover the different aspects related to the additive manufacturing first. So in which we will see the definition of additive manufacturing and the different types of additive manufacturing processes and steps. Then after we will discuss the challenges, what kind of challenges are coming into the additive manufacturing domain and how can we overcome them. And then we will see the how can we overcome the challenges with the help of hybrid approach. If we apply this hybrid approach in additive manufacturing, then how the challenges can be overcome. So this will be basically the theme of the today topic. Then I have some case studies. So those case studies I will share with you what I have done in this area. And then if time will permit me, then I will share my some other research work which I have done in the area of additive manufacturing. So what is additive manufacturing? So as you all aware with the 3D printing process, because commonly people call it 3D printing. So 3D printing or additive manufacturing. So generally in technical term is not 3D printing. Technically, if I call this process, then this is additive manufacturing, right? So what is it? So according to the standard ASTM F42, the process of joining materials to make objects from 3D model data, usually layer upon layer, as opposed to subtractive manufacturing methodology. So basically, according to this particular standard, additive manufacturing is a process of joining different materials. So material can be same, or we can use different materials to make a three-dimensional object, right? So here initially we need to have a 3D model data, and then we can use that particular 3D model data to generate some sort of information that is required for additive manufacturing, and then we generate the different toolpath information or that is required to add materials in layer by layer manner. So basically, if I compare it with the subtractive manufacturing methodology, it is totally opposite to that. Why it is opposite to that? Because here we are adding material. So initially we are having very less volume, then we are keep on adding layers and layers and layers in the z direction until the part is completed. But however, in the case of subtractive manufacturing, we start with the larger workpiece. Then we remove material in the form of chips. So a small amount of material is removed until we get the desired object or desired dimensions. So it is totally opposite to the subtractive manufacturing, and because due to the layer addition, the advantages with additive manufacturing means basically the advantage which we get from it, that is the complexity. So more complex part can be fabricated with the ease with the help of this particular manufacturing process. Okay, so those aspect or those feature which cannot be fabricated with the help of subtractive manufacturing, we can fabricate them with the help of additive manufacturing with ease. So that's why people are more focusing in this on this area. So a lot of research is going on, and people are working on different additive manufacturing processes, and they have come up with their own unique ideas. So in this series, people have come across with the hybrid approaches. So they have applied some conventional manufacturing methodology in the area of additive manufacturing. So that's why this idea have come into the existence, that is hybrid additive subtractive manufacturing, right? So if I overall summarize the additive manufacturing, so it's a kind of digital fabrication. So it takes a model. Okay, model means three-dimensional data. That is nothing but the digital design. So first we prepare this digital design in a software. So there are various softwares available which can be used to make this three-dimensional data. Okay, or else we can get it from the website. So there are many websites today which are having readily available CAD model data. So we can download the model from there and we can make a three-dimensional object from the scene. So overall, basically, with the help of additive manufacturing, we can turn the digital design into a real physical object. So basically, overall, if I say, then we can convert our idea into reality with the help of 3D printing or additive manufacturing. So in this particular picture, you can see how we are adding material in the form of layer, and our model is being fabricated with the help of material, right? So initially we are starting from the less volume, and then we are adding for material. So materials keep on adding until we get the final object. So this is the definition of additive manufacturing, and now we have seen the features of additive manufacturing and how it is different from the subtractive manufacturing. So what is the process chain of additive manufacturing? What are the different steps which we have to follow in order to make a three-dimensional object with the help of additive manufacturing? So first is the CAD model. So here I have mentioned all these steps which are required to make an object with the help of additive manufacturing systems or the processes. So first is the CAD model. So as I told you, CAD model can be made with the help of the softwares, or we can take it from the website. So there are many websites, okay, therefrom we can download it. If you want any modification, then you can do it, or else we can use reverse engineering techniques. So you might have heard about the reverse engineering, and some of you have some knowledge about the reverse engineering. And what is reverse engineering? Means if we have a real object, then we can do scanning, and then we can collect point cloud data from that. Then we can go for the CAD modeling. So first step in additive manufacturing is the CAD modeling. Then after we go for the tessellation. So tessellation, what is it? It is the conversion or the approximation of the CAD model with the help of triangles. So you can see here we will get the here we will approximate the surfaces of the CAD model with the help of triangles. Okay, and this is done because we need to slice this data in the next step. So slicing it is a bit easier if we feed this tessellated model in the slicing software. So tessellation is required in the additive manufacturing if you want to slice the model. Okay. Then after slicing, so next step is the slicing. So what is slicing? Slicing means to extract the contour information along the Z direction, because it's a layered manufacturing. So here we are adding different layers together. So that's why we have to generate the contour information or the layered information along the Z direction. So in the slicing, we can get the contour information with the help of the software. So there are various software, very dedicated softwares are there, which can be used to get the contour information from the tessellated model. So tessellated model is also known as the STL file, is standard triangulation language, right? Then after slicing, we go for toolpath generation. So toolpath generation means, because now we have contour information or contour data, now we need to fill it. So various area filling patterns, various patterns are there which can be used to fill the area of the contour. So we can go for the raster pattern, we can go for the offset pattern. Okay, contour of means we can offset contour until we get the filled area. Okay, fully filled area. And also we have piano curve, we have fractal curve. So there are various curves are there that those can be used to make the to generate the toolpath or to fill the data, contour data along the z direction. So after generating toolpath information, we feed this information to the machine, and then after part fabrication is started. So then after we get the actual part or the real part. Okay. Then if post processing is required, then we can go for the post processing. So in which we can remove support material, we can go for the smoothing of the surfaces and other tasks. So these things can be covered later on after the part fabrication. So this is a typical cycle. Typical means why I'm saying this typical means process chain. I'm not saying all the steps will be followed in each additive manufacturing system. Some of the system may be skipped. Okay. But more or less all are required to make an object with the help of additive manufacturing systems. So where means you can perform research in this area, means where you can which area can be targeted by you. If you want to pursue research in this area, then what are the different areas where you can start your research? So this is the last one, means the post processing. Why I'm focusing on it? Because it's very, very important. Okay. So post processing means can be done with the help of the subtractive manufacturing. So I will cover some of the things later on. Okay, means in the coming slides, and also there are some more topics that can be covered with the help of hybrid additive approaches. So I will be going to cover those topics in detail with you all. Okay, but before proceed to further toward the hybrid additive subtractive manufacturing, let me discuss the different techniques of additive manufacturing. What kind of techniques are available? So first is the FDM. Okay, so it works on the principle of material extrusion. So it's quite similar to the injection molding machine, in which we use a nozzle and a mold. But here mold will be missing. We will use nozzle only, which will be used to deposit material on the substrate or the build platform in a predefined pattern. So material extrusion, this is the first principle that is generally used, and this is very popular among the researchers, among the industrialists, because this process or this particular process is available at very low cost. So if you want to have a prototype, or you want to you need a additive manufacturing system for prototyping purpose and for the small functional parts, then you can go with the material extrusion based systems. Okay. Then second is the wet polymerization. So wet polymerization means here we will use the liquid form of the materials. So material will be cured when the material will be exposed to the UV light. So then we will get a SLA, then we will get the three-dimensional part. So in which there are different techniques basically. So two are very popular, SLA and DLP. And third one is the powder bed fusion. So SLS is one of the process that is very popular because it uses the powder based material. So fine powder particles are used to make a three-dimensional object. Okay. And next is the material jetting. So it is quite similar to the inkjet printers, okay, which we use to take print out on the paper. So here we use a jet that is used to inject the material on the build platform, and again we use UV source to cure that material, and then we get three-dimensional part from it. The next process is the winder jetting. So winder jetting means here we can make parts with the sand particles. Ceramic parts can be prepared with the winder jetting. So here we will not melt the ceramic particles, but here we will use binder. So that will bind the different ceramic particles or the sand particles in order to make a three-dimensional object. So this is the beauty of this winder jetting. we are not using any heating resource, okay, like laser or any other thing, but we are using binder jetting, binder, in order to bind the particles of sand or the ceramic. The next process, that is the extension version, we can say, of the powder bed fusion techniques, that is the powder bed fusion for metals. So in which there are various processes like DMLS, direct metal laser sintering, then selective laser melting is there, then electron beam melting is there. So nowadays people are exploring the metal based additive manufacturing system, because they know the limitation of the polymer based additive manufacturing system, because they are only suitable to the prototyping. So if you want to do prototyping, then only you can go with the polymer based additive manufacturing systems. But if you are looking for the objects, they should have good strength, adequate strength for some particular applications, then we should go with the metal based additive manufacturing systems. Okay, means if you if you want to have a object for some realistic applications, then we should go with the metal based additive manufacturing system. Okay. So now, what are the challenges? What are the challenges which are being faced by the research fraternity in this who are working in this area or the domain? So first is the material constraints. So overall, if I summarize the challenges of the additive manufacturing, then first challenge is the material constraints. Because if you take an example of any system, for example FDM or a normal 3D printer, so only specific range is available. Specific range means very limited range is available in terms of the material. Like you will get the polymer filament of ABS, PLA, nylon, and the some composite filaments are there, but this range is very limited. So this is the first challenge which we face in additive manufacturing. Then second is the part size limitation. Part size limitation. So second, basically the part size limitation means if you have seen a 3D printer, then you might have observed the size of the build platform, because size of the build platform is very less in the case of 3D printers. It is only about 200 by 200 by 200 mm. So only this much working volume is there, or by 300 by 300, or 600 up to 600 1 meter. So if you looking for a part with bigger size, then you cannot fabricate on the current 3D printers which are available at low cost. So this is the second challenge which we are facing in the area of additive manufacturing. And third one is the limited toolpath. But nowadays researchers have incorporated some new toolpaths in the 3D printing softwares or the additive manufacturing softwares. But still this is one of the problem. Most of the people use the raster pattern, so where they deposit material on the linear patterns, like 45 first layer is deposited on 45 layer, and another layer is deposited on the minus 45 degree angle. But as a researcher, sometimes we require different types of pattern to make the specimen, okay, testing specimen. So for that we can go with some other toolpath patterns. So this is another challenge. Limited toolpaths are there. So you need to explore some of the new toolpaths, okay, patterns that can be used to fill the area of the contour. Then next challenge is the surface finish, because we are adding material in the form of layers. So different layers are added in order to make a three-dimensional object. So that's why, due to this layer addition, the surface finish of the fabricated component is not that much good. So we need to apply some post-processing technique in order to achieve the good surface finish. Right? So due to the layer addition, again the dimensional accuracy of the components is problematic. So we do not get the good dimensional accuracy with the additive manufacturing, because there are various factors. At what temperature we are depositing material, right? Which pattern we are using to fabricate the part. So there are various factors which play a very important role in the dimensional accuracy of the components. So here I have taken one example and I have shown this figure to show you the surface finish of a metal component that is fabricated by the metal based additive manufacturing system. So you can see the surface of this component. So that is very poor. So if I compare a component, if I compare this component with the component of the conventional manufacturing process, then you can see the surface finish quality. So in this case, the surface finish of the components is very, very poor. That's why we need to do some sort of post processing. We need to apply some of the techniques that can be used for achieving the good surface finish. And similarly, in this diagram, if you see, so surface finish can be improved by applying post processing technique, and also if we still want to improve the surface finish quality of the components, then we can go with the thin layers, because in these figures you can see this particular model is made with the thick layers. Okay, so build time will be less because since we are using thick layers. Thicker layer means are being used here. Okay, and if you look at this model, then this model is fabricated with the thin layers. So resolution is very, very high as compared to this one, right? So what we can do here, if we go with the thick layers, so what is the advantage with this? Our build time will be reduced, or we can fabricate part at minimum time, or in the minimum build time than that of thin layers. But what is the problem? Poor surface finish. The surface finish of the component will be very poor. So what we can do, we can use thick layers to make the component. Then after we can apply post processing like machining. So if we apply machining technique on it, then we can improve the surface finish. So here now onwards, I will show you some of the case studies. Is how this hybrid approach can be used to overcome some of these challenges. So first one is the material constraint. So material constraint, how we will see how can we overcome this particular challenge with the hybrid approach. Then after we will move to the part size limitation, then we will move to the limited tool path and surface finish and dimension accuracy, right? So first case study is the retrofitment of CNC milling machine or machining center in order to overcome the challenge of material constraint. So before I go into detail in this particular case study, first let me introduce this FDM process or a triple F process to you. So what is FDM or triple F? Is what is the working principle of it? So here what we do, we use the material in the form of filament. So here I'm just considering this particular process in my case study. Okay, and we will see how can we overcome the material constraint of this triple F, right, with the hybrid approach. So if you look at this particular schematic diagram of triple F process or FDM process, then you will see here we are using the feedstock or material in the form of filament. So filament is feeded through these rollers. So we are having these rollers, right? And then we are feeding material with the help of these rollers to the extruder head. So this is the liquefier. This is the liquefier head or the extruder head, right? So this is our extruder head. Extruder head. So it has the heating element, and then it has the nozzle and other elements, okay, which are supporting the extrusion mechanism of the material. So here from we insert filament. So here from is from the top. So from here we insert material in the form of filament, and then these rollers are used to feed the material into the opening. So here we are having opening, okay. So into this opening we insert the filament with the help of these rollers. So after, because the heating elements are there, so due to this, material will be extruded from the nozzle on the substrate or this build platform in the form of layers, right? So why I am focusing on this slide is what is the purpose? What is the purpose? So purpose is that for triple F or FDM, if we want to fabricate a three-dimensional object, then we need to convert material in the form of filament. First, we need to prepare a filament. And what kind of property should be there? First property is the filament should have the uniform diameter. So diameter may be 1.75 mm, it may be 3 mm. So it depends on the machine, what kind of machine you are using. So generally in our country, we use filament with 1.75 mm diameter. Okay. So preparation of filament is very difficult for us. So this is the first problem. Okay. If you want to explore a new material, for example, suppose currently only 10 materials are there in the library of FDM or triple F. Now you want to extend it, means you want to add some new materials into the library of this particular process. Then what you need to do? First you need to convert. First you need to select the material. We should have the specific property. Okay. What kind of properties? Means it should have the adequate strength. Adequate means adequate ductility, because we are going to convert the material in the filament form. So first we need to explore material or the suitable material. Precisely if I say, then we need to select or we need to find out the suitable material for this particular process. Second one is we need to convert the material in the form of filament. So filament fabrication is not an easy task, because diameter is very specific. You need to fabricate a filament with uniform diameter of 1.75 mm. So there may be some tolerance, okay. So minor variation can be permissible, but still you need to fabricate filament of 1.75 mm diameter. So due to polymer swelling and lot of factors are there, so it's really difficult for us. If you are looking looking for the fabrication of filament, then it's really difficult. If we need to control the various factors, and we need to extrude material in the controlled environment, then only we can achieve it. And second one is the mechanical property of the material, because I have told you about the opening, because here we are having very small opening, right? If the material is not having that much column strength, why I am calling it column strength? If you consider the filament from this point to this point as a column, if it is not having the adequate column strength, then we cannot feed this filament through the extruder head of triple F. So what will be the problem? Let me show you. Let me describe you this particular challenge in the next slide. So low column strength, if adequate column strength is not there, then what can happen? We can face some challenges in the printing of flexible material, because flexible material means those materials who are having the low column strength. So this is one of the challenge, low column strength. Second, so it will lead to the it will lead to failure of part printing with highly flexible materials. You can see buckling is there. So buckling occurs when we try to feed the highly flexible filament through this particular feeding mechanism. So what we can do? We can go for some other processes, or we can go for some other approaches. So why here means we are having buckling in between the this opening and the roller. So what will happen due to this buckling? Because filament itself actually works as a piston. When we feed it into this particular opening, then what happens? This filament acts as a plunger which pushes the material into this opening. But due to this flexibility and buckling, the filament itself will unable to produce appropriate force for pushing viscous melt against the nozzle opening. Because here we are having the nozzles at the bottom. Okay, so material extrusion takes place due to the strength of the filament, column strength of the filament. If the filament does not have the adequate column strength, then we will not have extrusion at the exit of the nozzle, because filament will be unable to produce appropriate force that is required for pushing viscous melt. Why I am calling it viscous melt? Because it is inside the extruder head opening where heating elements are there, so we will get the viscous melt. So it will unable to produce the appropriate force for pushing viscous melt against the nozzle opening, because very small opening is there. So we need to push the material. We need to apply more the pushing force on the viscous melt. So that's why the flexible filament will not act as a plunger. So this will be the problem. If we suppose if you are exploring the flexible material with the help of the triple F, and material is highly flexible, then you cannot make 3D-dimensional object with the help of triple F processes. Okay, so what we can do means, what is the answer? How can we make flexible components with the help of hybrid approach? What is the answer? Answer is that retrofitting. So retrofitting means adding of new module to an existing CNC machining center. So suppose you are having a CNC machining center. So this is our CNC machining center, for example. CNC machining means CNC milling machine, or any machine is there, can be there. So if we are adding any module to this machine for additive manufacturing purpose without disturbing its original functionality. So actually means the work of the CNC machining center is to remove material from the stock. But what we do, we are adding a new module without disturbing its original functionality. So it means that we will enable additive manufacturing, or the machine will be enabled with the additive manufacturing process, and then we can fabricate parts, 3-dimensional part with the different materials. So how can we do it? So what are the possible methods if we are doing retrofitting, if we are adding a new module into this CNC machining center, then what are the possible methods that can be used to print flexible parts? because in this case study we are targeting on the printing of flexible parts. So what are different possible methods we can have? So first means problem, that is the with the filament. Okay, so what we can do? So instead of filament we can use polymer pellets. So polymer pellets can be used for direct extrusion as well as deposition to fabricate flexible parts. Okay. So first what we can do? We can go with the pellets. So instead of filament preparation, we can go with the direct extrusion of the pellet. So this is the first method that can be used. Then again, because we are going to use pellets, so we need to develop a system that can process the flexible as well as rigid polymer materials, because now we are having possibility to use flexible material along with the rigid polymeric material or the other rigid materials and their composites. So because we are doing means retrofitting here, so this module can have facility. This is the module, okay, which we are adding to the existing CNC machining center. So this module, with this module, what we can do? We can develop a module which have the facility to facilitate the flexible as well as rigid polymeric materials. So this is means a condition that can be used to make or to develop a new module for the existing CNC machining center. So with this objective, what means we have done in this area, we develop a material deposition tool. So this was a module, okay, this was a module. So this was developed in order to fabricate the flexible components along with the rigid components on the CNC machining center. So this particular module was compatible to the CNC machining center. So we had this CNC milling center or CNC milling machine, that is the make of the Okuma. Okay. So what is the characteristic of this particular module? It was easy in mount and demount. So whenever you want to dismantle from the CNC machining center, you can easily dismantle it. So whenever it is required, you can again mount it on the CNC machine at the place of with the help of a spindle. So you can see schematic diagram of this particular setup. Here I have shown to you. So here we are having spindle, and here we are having material deposition tool, and here at the bottom we are having part being printed. Right? So what we have done, we have added this build platform on the table of CNC machining center, and with the help of a spindle, we have added this material deposition tool or the module to the CNC machining center, and then we have fed the material in the form of pellets. So you can see there is hopper. So there is hopper in which we have fed the material in the form of pellets. Okay, and we have used heaters and different components we have used there in order to extrude the materials in the form of wires. So this is the actual picture. This was the schematic diagram. This was the schematic diagram, and this is the actual picture. Right? So this particular setup was fabricated at IIIDM Jabalpur. So with the help of water jet machining and CNC machining and different manufacturing processes we have used to fabricate this setup. Okay, and the hopper was made of the filament based additive manufacturing system, that is FDM. So as per the requirement, we have used different manufacturing processes to develop this setup. And this setup was mounted on the CNC machining center that was available at IIITM Jabalpur. Right? So what are the different components this particular tool is having? We were having this standard CNC tool holder. Okay, so this was available with CNC machining center only. We have not made this. This was standard CNC tool holder that is used to hold the milling cutters. So we have used the same for our work, and then after we have designed this hopper, then we have made this screw and barrel, and then after band heater we have used, and nozzle we have developed, and then after this supporting frame. The supporting frame was developed with the help of water jet machining and other manufacturing processes. So initially we try to fabricate parts with the rigid polymer materials, because we knew about the ABS. So initially, because we were having idea about the ABS material, so initially we try to extrude this ABS material with the help of setup which we have developed. So because it's a very new process for us, so that's why we had a lot of issues like blockage at the entrance of the barrel, and bearing extrusion diameter we were getting from the nozzle, and also material was degrading due to excess heating. So after doing a lot of experimentation, we developed know-how on the CNC machining center with this setup, and then after we have optimized some of the process parameter in order to get the quality extrusion of the material from the nozzle. So since we know that the softwares which are readily available for the CNC machine centers, they are dedicated for the toolpath generation, but they can generate toolpath for milling purpose or the machining purpose only. Means if you want to use them, those softwares, then they have facility to generate toolpath for machining purpose, for machining of the components. It means that if you feed CAD model into those softwares, then you can generate the cutter toolpath information. Right? So there were no facility with the softwares. So what we have done, what we did in this area, so we developed our own software. So why we have developed this software? Because we did not have any facility to create G and M codes, toolpath for additive manufacturing. So that's why our requirement was different than the machining. So that's why what we have done, we have developed our own customized software module, and then we merged all the necessary steps for generating toolpath for deposition of the material. So in order to ease the operation, or in order to make it easy for the operator or the user, we developed the graphical user interface. So this kind of user interface was developed. Okay. So here just user has to give some values corresponding to the options available, like STL. He can user can import STL file. User can slice the STL file which we have imported earlier, and then user can generate toolpath. So different toolpath options are there. So we can select the different toolpaths pattern. Then we can create G and M codes, and these G and M codes are compatible with the CNC machining center. So if you want to reset all the parameters, then we have facility to reset all the parameters. Then again we can change the value. So you can see initially we fabricated this kind of object. Okay. So we imported this STL file into this graphical user interface of the software, and then we have generated the GM codes, and then the GM codes will be have uploaded to the controller of the CNC machining center. Then we fabricated this kind of component or this sub component with the help of develop setup. So initially, if you look at this diagram or this picture, then you will find very poor surface finish and dimensional accuracy. But since these are the these were the initial results which we have got from the experiments with the develop setup. So here again the different features of the develop customized software modules are presented. So import and processing of STL files can be done with these. Then slicing can be done. Then after toolpath generation that is compatible to the CNC machine center can be generated. So you can see the slicing. So all these slices of this particular model are clearly visible to us. So along the Z direction, we could perform the slicing and we got the control information. And after getting control information, we filled the area with different toolpath patterns. So this is the standard basically raster toolpath pattern which we have shown here. Okay. And this is the GM code or the toolpath which we have developed for the CNC machining center. So all the code which we have used through in this program, like S130, G01, G00. So these are the codes which are accepted by the CNC machining center. It means these codes are compatible to the CNC machining center and can be used to fabricate the parts through additive manufacturing approach. So I think process video is missing as of now because it's having very large size, so that's why I am unable to play this video as of now. Okay, but you can see the close view of this particular setup. So after ensuring the processing of rigid polymers through the developed setup, we have explored the flexible materials. So in order to make the flexible parts on the developed setup, we have chosen this ethylene vinyl acetate EVA material. So why we have chosen this? Because it's elastomeric material which is very flexible in nature. So you can see, you can look at the pallets of the EVA or EVA. So they are transparent and they are flexible, very soft. So we have extruded initially these pallets and we have prepared this kind of filament from the nozzle, or we were able to extrude material in the form of filament. So initially we did not try to make the different parts with the help of EVA. So after ensuring the perfect extrusion from the nozzle, we have gone for the part fabrication. So part fabrication was done based on the process parameter study. So this study I am not going to cover in detail here because I need to I will show you some more case study. That's why process parameter study in detail. Okay. So after performing this process parameter optimization, we fabricated these kind of flexible parts. So you can see the quality of the fabricated components. So see how flexible they are. So I have demonstrated the flexibility by hand, you can see. So these are my hands. Okay, so I am just twisting it in different directions. So I am twisting it in different directions. So initially you can see this is a tensile specimen which is made of EVA material. So you can see how flexible this specimen is. I can twist it. I can twist in different directions. So this twisting shows that the part fabricated with the EVA material were very flexible in nature, right? Then we have gone for the mechanical testing. So in order to check the flexibility, first we wanted to ensure the bonding between the raster. Is what is the quality of bonding? So you can see here I have taken the microscopic view of the deposited rods of EVA material. So you can see the very good bonding between the rasters was obtained, right? Then in order to test the elasticity of the materials or flexibility within the materials, there was a standard test, hysteresis test. This test was conducted in order to check the flexibility of the specimens. So in this test, the specimens were elongated up to a certain percentage of the length and then relaxed. Then we left them. Why? Because they were flexible in nature, so they gained their original shape after a certain period of time. So through this testing, we calculated the residual deformation. Residual deformation. So after collecting the data, we have plotted this graph. So you can see this is the graph between the deformation percentage and the residual deformation. That is again is in the percentage. So you can see here there is only 0 residual deformation up to 30% deformation, and for 60% deformation only 1% residual deformation is there. So it means specimens were getting their own or original shape up to a certain range. So after fabricating the flexible components of the EVA or the EVA material, we explored our study toward the flexible electrically conductive composite parts. So why we have attempted this study? Because based on the literature, we came to know the different application of flexible electrically conductive composites. And the application of these kind of composites have increased over the time, like in the health monitoring, displays, pressure sensors, and flexible circuit fabrications are some of them. So here again we have used EVA as a polymer matrix, and then we added graphite as a filler material, right? So here I have taken some of the picture which are showing the application of these kind of composite materials. So stretchable electronics are in the use. The stretchable conductive paste developed by DuPont, and then a new conductive felt carries electricity even when twisted and when stretched. So these kind of products are in the market, and they are having various applications. So that's why we went to explore this kind of composite, because our setup was compatible with the flexible materials, and we were not fabricating any filament as a raw material. We were directly feeding the pellets of the EVA. So we added graphite material with different weight percentage, and then this kind of methodology we have used to make the electrically conductive polymer composites. So graphite powder was added into the EVA solution. So first we prepare the solution of EVA with the help of solvent cyclohexene. Then we stir this solution of the graphite and EVA for this particular time. Then after we have poured this particular solution on the flat plate. Then we waited till the whole solution get dry. Then we have pelletized this solution. Then in order to remove the solvent from this particular material, we kept this material in the furnace at some particular temperature, right? Then after ensuring the removal of solvent, we fed this material into the double up setup or double up module of the additive manufacturing. So we have fed this material and then we fabricated this kind of components. Now what our aim was to test the specimen for electrical conductivity. So we have tested the specimen for various through various techniques. So SEM we have done, we have performed XRT, we have performed the FTIR techniques to check the structural and the morphological changes with the addition of graphite into the EVA, right? And also we observed the rheological behavior of the material, because based on this rheological behavior we decided the value of road gap, deposition speed. So there are various factors in the additive manufacturing. So these factor values values of these factors were decided based on the different techniques, the rates of different techniques. Then we fabricated the tensile specimen as well. We have fabricated the specimen for electrical conductivity, and we fabricated the specimen for compressive properties, right? So this specimen, disc cave specimen you can see here. So this was fabricated for the electrical conductive testing, and this was the tensile specimen, and this was the specimen for the, I forgot, for bending test. I think we have tested this specimen for bending, and this one for the compressive properties. So you can see how flexible these specimens are. So I bend them in different directions. Okay. So after addition of graphite into the EVA, specimens were still flexible, but the flexibility was very less than that of EVA. So we have tested these specimens for electrical conductivity with the alpha 4 probe method. So what we have got with from the results, the conductivity of the specimens which we have fabricated, the electric conductivity was increased when the graphite percentage was around 30%, 38%. So almost 39 times increase in the electrical conductivity was observed with the EVA with 58% graphite than that of neat EVA. So these were the improvement which we have received, which we have obtained with the help of the composite material. However, on the other side, tensile properties were degraded. So why they were degraded? Because due to the poor bonding, you can see there is space between the different rasters. So poor bonding was there because flowability was affected with the addition of graphite into the EVA. So these kind of pores we have observed in the SEM images right? So that's why it affected the tensile properties like the tensile strength and elongation at break. Then compressive property, again we have seen the increase. We have seen the increment in the compressive property. So you can see there is was jump, okay, in the compressive property of the specimens, and an increase of 172.5% was reported. So why it was happened? Why it is so? Because graphite is stronger candidate than EVA. So which bears the compressive load conveyed by the EVA matrix. Okay, so that's why it increases the load bearing ability of the composite specimen. So the case study which I have discussed with you, that was for the flexible part fabrication with hybrid approach. Another thing which we have tried with this approach, that is hybrid additive subtractive manufacturing. So in this particular study, what we have done, we have used this tool for the finishing purpose or for machining purpose. So first we have done the additive manufacturing or printing of the part, and then after we have applied the machining operations. So you can see here I have first we have fabricated this one, and then we have applied the machining process. So you can see here the surface finish. If you compare this surface, suppose surface number 1 and this is the surface number 2. So which one is having better surface finish? This one, because we have applied the machining on the fabricated component. So outer surface of the components was improved with the help of machining operations. But there are some problem. When we thought of this particular process, then what kind of problems were there? This was the problem, because initially we have developed the customized software module for additive manufacturing, but now we needed to extend this particular custom software module for subtractive manufacturing too. So what we did, we extended the software module toward the subtractive manufacturing too. So initially our software module was having this facility of additive manufacturing. Then we have added this facility. So at the same time, when we were preparing the toolpath for additive manufacturing, at the same time we were preparing the toolpath for subtractive manufacturing. So first just we need to feed the these values like cutter diameter, step over, okay, and also we have explored a new kind of toolpath approach for machining operation, because we know the quality of additive manufacturing. Quality means the capability of the additive manufacturing, because it is having capability to produce complex shapes. So if complex part is there, then how to machine it? So this was the main challenge. So what we have done, we have explored a new kind of toolpath strategy. So that particular work is not published yet. We are working on that, and it will be published very soon. So you can refer that later on. Okay. So this was the first. This was the module which was developed to enable the additive and subtractive manufacturing on the CNC machining center. Right. So you can see this is additive manufacturing, and this is for subtractive manufacturing. Now here I have taken some of the pictures to show you the capability of the develop process. So initially you can see this kind of component we have made with the additive manufacturing. So you can see some of the problems at the corners, okay, due to the acceleration and deceleration of the nozzle, or the stopping and the starting effect. After that, we have applied finishing technique. So this is after finishing. .495 micron, and after the machining operation, it was reduced to the 2.068 micron. So this kind of improvement we have obtained with this approach, hybrid approach. Then after exploring this hybrid additive subtractive manufacturing, we have gone for the large part fabrication using CNC. Because as I have discussed with you, the part size in additive manufacturing is one of the challenge. So what we have done here we have explored the same setup for the large part fabrication. So what we have done, first we have designed and developed a build platform of bigger size. Then after we try to fabricate large size object. So you can see here we are having some large objects, okay, like up to 600 mm. So on the same build plate, sorry, on the same table where we have done additive manufacturing for the small components, we have enlarged the build platform size, right? Then we have made this kind of objects. So these are the large size objects which were fabricated with the help of the same setup. So this is another advantage with the hybrid approach or with the developed setup. If you could fabricate the parts with large size, or the bigger size parts could be fabricated. And further, if you want to increase the size again, then you can further increase the build platform. Then, but you need to understand the process again, because for large size parts there are a lot of problems. Warpage is there, heat dissipation is a big problem, bonding between the layers, because the completion of first layer takes a lot of time, then another layer. So for example, if 500 layers are there, then imagine how much time it will take to complete the whole part. So build time is another problem, but we can explore this process toward this direction for the large part fabrication. Okay, these are this is another part. You can see the size here. I am mention the scale, but this size, the part is again is very having a very large size, and you can see the toolpath pattern. So on the boundary or on the the cell of this particular layer is solid, okay, is filled completely. However, the inner area under the cell is filled with different toolpath pattern. Okay, so porosity is there. So deliberately we have used this kind of toolpath in order to save the material and time. And another hybrid approach for another work, we can use hybrid approach. One challenge I told you about the toolpath patterns, limited toolpaths. So why here we have explored the fractal type toolpath pattern through this retrofitting in the additive manufacturing. So why we have explored this fractal? Because what is the problem with rasters? If you see, if we have long rasters, suppose nozzle is going to deposit material along this direction, for example, then again it will come back through this path. So what is the problem in this? Because due to this length, because it's long raster, okay, for example 200 mm. So nozzle is starting depositing material from this point, and it is reaching up to this point. So 200 and then 200. So what will happen? Due to the time difference, or due to the large time difference between these two, the bonding or the temperature between these two rasters will be having large difference. So temperature gradient will be very high. So you can see the color coding. The fourth one, this is the red color, having red color, and this is like pink color. So this color is showing the temperature difference between these 2 points. So due to this temperature variation, the bonding between these two will be poor. The bonding between the rasters will not be good. So what we can do? However, in this case, the temperature gradient will be less. Here we are having temperature gradient very high, and here it is very less. So it means you will get variable bonding within the layer. Suppose this is your one layer. So here you will get different kind of bonding, and here you will get different kind of bonding. So variable bonding will be obtained, or will be there due to this tool path pattern only. So if I fill my layer with different tool path, then what will happen? So here you can see again, this is the fractal approach. So you can see very short rasters are used in the fractal based approaches or toolpath approach. So it overcome this situation. So here we have obtained the good or the superior tensile properties than that of raster one. So you can see, so this kind of toolpath was explored with the help of this hybrid approach. Okay, so just I think now time is not permitting me to discuss more case studies with you. So I think let me stop at this point. So if any queries there, then you can you are most welcome to ask.
Yes, definitely. Thank you so much, Professor Kumar, for this much wonderful discussion with the participants. It was really a very nice talk we had. So, dear participant, you are requested to ask the queries if you are having any. Okay, you can ask your queries by raising your hand. Okay, so we can permit you to unmute yourself, or either you can write your queries. Okay. So we are just waiting for a few seconds more, so you can raise your hands, or even you can ask by writing. Okay, I think participants are feeling more satisfied with the discussion of yours, sir. Okay, so dear participant, so it's a time to conclude this particular session. Thank you so much, Professor Narendra Kumarji, for having time with us. Okay, so we are very highly grateful to have you over here. Thanks a lot for being with us. Okay, so we feel pleased to have you during this technical session. So dear participant, we are just now concluding the day. It was the 4th day of this AICTE Atal Academy, FDP, on hybrid machining solutions for complex and typical engineering applications. Okay. So we will meet tomorrow. So, okay, thank you so much. Thanks a lot.
Thank you, sir. Thank you very much for inviting me.
Welcome, sir. Okay, participant, you can leave. So it's the end of the fourth day. Thank you. Thanks all.